Okay, welcome everyone to day 2 of the symposium. This morning session will be about new frontiers in time domain science, and our first speaker will be Mansi Kasliwal, who will tell us about highlights from ZTF. Please go ahead.
Thank you. I just wanted to start with thanking our wonderful organizers, Ragnhild, Klaus, Ariel, Jesper, and Anders. It's been a very stimulating and engaging couple of days, actually all week for us. And thank you for all of you waking up after that wonderful dinner and the 400-year-old history to make it to a 9:30 a.m. talk. That's not bad. And it's nice it's 9:30, not 9. Okay. All right. So I wanted to begin this talk by giving credit to my graduate students and postdocs, current and former. And throughout the talk, I'll be crediting their contributions. There are 2 in particular that I wanted to call out who are in the audience, if I can get this laser pointer to work. The first is Sam Rose. Sam, please talk to her about any red transients, any JWST spectra, and the other is Kostov Das. Please talk to him about any type of supernova, particularly core collapse. Any flavor is good. The lower the mass, the better. He'll be more excited. And throughout the talk, I'll be crediting their contributions. This is by far the biggest pleasure and privilege of being at Caltech. And I also wanted to thank my various collaborators in different organizations. Several of the things I'll be presenting are works of large teams here. So at Caltech, as far as the time domain goes and discovery engines go, I'm surrounded by excitement. At just about every wavelength, there's sort of some next frontier, game-changing discovery engine in the time domain that is being built as we speak. So my friends Greg Hallinan and Vikram Ravi are working on the radio frontier with pushing from DSA 110 to DSA 2000. I've been most focused so far on pushing and opening up the infrared for time domain exploration. And I'm particularly excited about Cryoscope, which is a fully cryogenic telescope that we're taking to the Antarctic later this year. In fact, on October 28th, we have a boat from Hobart to Domesday and Concordia. So please feel free to talk to me about that during the breaks. And the focus of today is the optical revolution from PTF, which was my graduate thesis project many years ago in the Stone Ages now, to ZTF today, which is an industrial scale experiment that we've already been hearing a lot about at this meeting. And my colleague Fiona Harrison is now leading the UVEX project to revolutionize the ultraviolet. Yesterday we heard some fun things about Anna in the microwave, and several people are also looking at X-ray and gamma ray in other countries, other parts of the world for the next frontier in time domain there. You saw this beautiful picture yesterday of Palomar Observatory. Anybody who hasn't been to Palomar, please visit. And if you're in California, this is a must-see. It's more important to go to Palomar than to Hollywood. The observatory is now 75 years old and is founded on the motto of George Ellery Hale of make no small plans, dream no small dreams. And we do our most fun things with the smallest telescopes on the mountain. So our beautiful 200-inch telescope is actually surrounded by 5 robotic telescopes now, which are doing fun time domain things. ZTF, as many of you know, has this wonderful 47 square degree camera. And 3 people can now fit inside the belly of the beast since it was cut open wider. And yesterday you saw some results from Dan Purley also on the SCD machine on the Palomar 60-inch. So these 2 telescopes are the heart of the ZTF system. So I was asked to give highlights from ZTF. So let me start with the publication statistics, which are just off the charts. ZTF only came online in 2018. We've only been running for 6 years. And as Matthew can attest to here, our project scientist Matthew Graham, it is impossible to give highlights of ZTF in finite time, right? I mean, how do you summarize 1,035 papers and some really amazing ones, which just in a few years have give us an H index of 59, right? Thankfully, this conference did have several members of the ZTF family who've given talks that are going to be much better than this one, I promise. Some more coming up. You heard about fast blue optical transients from Anna. You heard about our bright transient survey from Dan Purley. You heard about some fun supermassive black hole science from Suvi Ghazari. And Mickael and Marek and Nial are going to talk in this afternoon about cosmology and stellar science. Avishai spoke yesterday about some core collapse science. So there, you've been getting tastes and highlights from ZTF from many different people and many fun talks. But the most important thing actually I want to say on this slide is we have an existential crisis right now. So if you would like to join the fun, we are looking for new partners. Please talk to me. Currently, we're only funded to go through December 31st of 2024. We have a plan in place to run for a few more years, but we do need a few more partners for this to continue. So, but we are having a lot of fun and we want to continue to enable lots of great science. And I should say the 1,035 papers is not the ZTF team alone. There's actually a factor of 4 multiplier on what we as a team have done versus what the entire world and the entire community has done from ZTF Science. And that to me is the is really satisfying. I mean, that the products that we produce from ZTF, Tracy and Avery are sitting in the back row there. They are at IPAC working hard to run the pipeline every day. And the data products from ZTF are actually enabling science for the broad community. So that's the most satisfying part about ZTF. Okay. So for the highlight, the single highlight that I'm going to pick for this presentation, I'm going to give some highlights from the multi-messenger working group in ZTF and the fun we've been having over the last few years. I'm actually going to begin with the figure on the right here, which is the IceCube high energy neutrino detector, and some very new results from systematic follow-up of high energy neutrinos with ZTF. So here's a summary of all the high energy neutrinos from the IceCube experiment that were deemed of astrophysical origin. You can see them nicely in the north, very accessible from Palomar because you need to go through the Earth for rejection. And if you want to know more details about that, Marek Kowalski is in the audience and is an expert on this topic. So with ZTF, we followed up 42 neutrinos in the last 6 years, and 4 have yielded promising, compelling counterparts. Suvi Ghazari yesterday spoke about the tidal disruption flares, so I'm not going to repeat that, but I wanted to remind you that what was very interesting about the 3 tidal disruption flares, so it's not 1, not 2, but 3 tidal disruption flares, is that every time we found a high energy neutrino from a tidal disruption flare, it seems to be associated with a mid-infrared echo, and the timing somehow, strangely, is associated with the peak of that mid-infrared echo emission. So there's a method to the madness there, right? I mean, the first time, I don't think any of us believed it, but 3 times now, I think there's seems to be some association for sure. And the newest association is IC231004A, which appears to be associated with an interacting supernova. So let me tell you more about that. So this is just the overall schematic. Many of you are familiar with gravitational wave follow-up. Neutrino follow-up is similar. You get localizations actually really nice, only about a square degree or 2 square degrees. You drop whatever you're doing, you go map the area. You have several candidates, you follow them up, and you try to figure out which one is physically, spatially, and temporally coincident with the high energy neutrino. So this one in particular from October 4th of 2023 was associated with this very luminous and fast evolving transient. I'm sorry, I'm not going to remember to keep pointing to the screen. So you can see it peaked to about minus 20th mag and faded away in a few days. Now we heard a beautiful talk by Anna Ho yesterday on the whole zoo of animals in the luminous fast blue optical transient category, this LF pod category. And this seems to be sort of the faintest member of that zoo, but very closely associated with that zoo. When we got spectra of this event, what was fascinating was that you can see the dotted lines that Robert has put here. They show you the position of helium, and there's narrow helium emission. So this is an interacting supernova, but not your regular type 2n supernova, but your type 1bn supernova. So it's a supernova interacting in a helium-rich circumstellar medium. And these intermediate with helium features actually make the classification that of a type 1bn supernova, not quite an LF bond. And this is interesting because for many years, and I'm just giving you one example here, people have theoretically proposed that interacting supernovae should be a prolific site of high energy neutrinos. And this is one example of a model from Kota Moraze at Penn State, which quantifies what sort of neutrinos should you get for different properties of the circumstellar medium. I think none of these models particularly care whether the medium is hydrogen rich or helium rich. You just need the medium to have a certain density profile and certain properties that can help accelerate particles and give you high energy neutrinos. And in the 42 campaigns, we've had exactly 0 type 2n supernovae that have been coincident. Way back when, when Iran Offutt was looking at some of these things, there was a candidate type 2n supernova, but I don't think it had enough evidence to claim a firm association. And now, many years later, we have this 1bn supernova that is very compelling in terms of its association with this high energy neutrino. And as I was mentioning earlier, this one is sort of right in the bridging the 2 categories of the luminous fast flow optical transients. And this here is a sample of type 1bn from ZTF that Jesper Solomon and students and postdocs in his group have compiled. And you can see it's a bit on the bright end for the 1bn and a bit on the faint end for these luminous fast flow optical transients. But there may be a clue here on what we call this wiki diagram, which is luminosity timescale. Zwicky loved morphological spaces like this, and we've seen many versions of this diagram in this conference already. All right, so now I'm going to switch gears from high energy neutrinos to gravitational waves. How many of you have written a paper on GW170817? This is the 87A question. Oh my goodness, there's very few hands actually. Okay, okay, only 50%. That means this is a young audience. Maybe you were still in kindergarten in 2017 or something. Okay, so I don't need to introduce this majestic event to you guys, right? 2 neutron stars merged. We formed a black hole, launched a jet. I do want to show you this beautiful simulation because we have Ehud Nakar in the audience, and I think his model of this simulation was made by his graduate student then, Or Gottlieb. And to me, this is one of the most beautiful results from GW170817 is understanding the energetics and kinematics via a mildly relativistic wide-angle cocoon, not just this ultra-relativistic, very collimated jet. And I don't know if Woody's going to touch upon this today or not, but please talk to him about this, this amazing breakthrough here. Now, since GW170817, ZTF didn't exist then. I told you ZTF came online only in 2018. The entire telescope was in pieces when this happened. We were commissioning. But since then, there have been the 3rd and the 4th gravitational wave observing runs. And very diligently, every time LIGO has issued a gravitational wave alert, ZTF has dropped everything it's doing and used its mighty camera with its 4,000 square degree per hour mapping speed to map localizations no matter what the size. And people have complained, it's 4,000 square degrees, it's too much. LIGO is producing very close localizations. We didn't complain, we just went and mapped whatever we could access without the sun, when the sun didn't get in the way, and when we didn't have to look through the floor. So our only limitations were the sun and the floor, okay? And the location of Palomar is particularly suitable for this work. This is actually real data from GWTC3. And as we had simulated, just because of LIGO's quadrupolar antenna pattern and the fact that the LIGO Hanford and Louisiana interferometers are much more sensitive right now than their Italian counterpart, the localizations either directly above North America. So our response time has been minutes, right? I mean, the localizations just happen to be in the same night sky where Palomar is located. So we've been able to do this exercise of mapping large areas with minimal response time, going through millions of candidates, right? And shortening the list down to hundreds, and then very, very diligently for every single candidate, getting photometry, getting spectroscopy, saying, this is not it, this is not it, this is not it, over and over and over again, to leave no stone unturned. And we did this again in 04A, which ran from May of 2023 to January of 2024. This was a set of events there. Very variable significance, some detected only by one interferometer. In 04A, we set a bar of false alarm rate better than 1 per year to follow up events. We also came up with this new scheme where we didn't interrupt the ZTF survey to do the TO follow-up. We just reweighted our survey. So our camera and our mapping is so fast that without a gravitational wave trigger, you see these gray fields here is what we would cover on a given night, just for a regular cadence survey. And when there was a gravitational wave trigger, we would just reweight it and focus on the huge localizations. This is a horrendous localization with just one interferometer. So this reweighting strategy was sort of minimal impact for the other science cases that ZTF was doing. And when there was only a single interferometer localization, we could do the follow-up and disturb minimal number of people when doing this. Now, the most promising candidate, I would say, so far in the 4th gravitational wave observing run happened on April 22nd of 2024. This event, at least as of today, has a false alarm rate of 1 in 10,000 years. There is some offline analysis happening, but as of today, it is very significant. And what is promising is that it actually has a 3-digit localization. Right? It's 441 square degrees. So this is a piece of cake when for the last few years we've been imaging things that are thousands of square degrees, right? I mean, here I show you examples from what Igor Andreoni and Antonella Palmese did with DECCAM and what we did with ZTF. But there were about 15 teams that went and mapped this huge area. And together, the community reported 88 candidates to TNS. And there was extensive follow-up done, a la 170817, to go and rule out and understand every single candidate. For us, this combination of DECAM and ZTF proved to be immensely powerful. Because DECAM could go deeper, but ZTF had this very high cadence, very long multi-year baseline. So the candidates on DECAM that looked very promising, if you just look at 2 points, could be ruled out as old supernovae if you went back and looked in the ZTF history. On the other hand, if the ZTF history was clean, there were no detections, and this candidate had popped up in DECAM, then we immediately triggered Keck and got a spectrum to see if the redshift was right and if this could be spatially or temporally coincident. So we were able to very effectively and very thoroughly do the follow-up by joining forces between DECAM and ZTF. And you should think, looking ahead, when you combine ZTF and Rubin, there's again potential for doing joint survey science that is not possible with one survey alone. So that was really fun, but everything was ruled out. Sorry, no kilonova. You guys need to be more patient for that. There will be another talk that talks about it. But before I move away from these 03 and 04 searches, I wanted to emphasize the importance of software. I cannot overstate the importance of this underlying software infrastructure that we use in ZTF, that we use for these sorts of follow-up. There are many, many tools that need to come together and many, many pieces of code that need to be put together to do a really, really thorough job of saying, yes, there is no kilonova in that data to a very, very high level of significance. It's not that we just missed it because, it was raining somewhere or we didn't get a spectrum in time. No excuses. There is no kilonova in these data in every square inch of the sky that we were able to map. And these tools have been a big focus over the last few years to make better, stronger, integrate. And I'm very happy to, again, have more detailed conversations about this with anybody who's interested. So if these non-detections are robust, then how do we convert these non-detections to actual limits on the underlying function, right? So if you're not finding anything, well, the rates are small from the gravitational wave side, but still, with whatever we have in hand, whatever hand has been dealt to us by the gravitational wave interferometers, how do we convert this to what we can constrain about the possibilities for kilonovae? So we've taken 2 approaches. One is an approach where we model in the frequency of the observations, the cadence, the depth, the weather, all of that. And we say, what does a non-detection tell us about the efficiency of recovering a GW17 0817 like event? So that's on the left, and that's about 36%. And then on the other hand, you can ask the question again on this feed rate versus peak magnitude, morphological phase space here. The Bayesian question, right? What is the posterior probability that we would detect an event like this? And happily, these two things are actually quite consistent, even though they're very different approaches to doing the statistics here. So we just published this in a recent paper. Well, it's submitted, it's being reviewed right now. And this can be inverted to constraining the luminosity function. We need a few more good, solid neutron star mergers from LIGO Virgo, from the International Gravitational Wave Network, for this to start to really touch upon models and constrain things like the underlying ejector mass and ejector velocity and so on and so forth. But at least it's a proof of concept here of how we can convert robust upper limits into these sorts of questions. Ooh, all the bars on this figure disappeared. Okay, no worries. This is Igor, who's in the audience, also has done some work on constraining the rates of these events. And independent of LIGO, we know that we are already at the point where ZTF can start discovering kilonovae independent of gravitational wave triggers. If 170817 was the norm, then the rate of these events is now less than, I think, 700 per gigaparsec cube per year as of today. So it has to be really, really low if we don't find one independent of the gravitational wave interferometers very soon. Now I'd like to switch gears a bit. We heard some lovely talks by Selma and Thomas Yanka yesterday on stellar evolution. Let's look at what happens before the neutron star merger. How do these compact binaries form? Since my former student Kishale is in the audience, I thought I'll pull up this picture from his thesis, where we really started to probe what type of supernova could lead to a compact binary that is compact enough to merge in less than the Hubble time. And during Kishale's thesis, he studied IPTA 14GQR, which was an extremely ultra-stripped supernova, such that you could make a binary that's compact enough to merge in less than the Hubble time. Since then, there have been multiple flavors of these ultra-stripped supernovae that we have found, with slightly more ejector mass, probably such that the stripping suggests that it's not so compact. Perhaps it doesn't merge in less than the Hubble time. Maybe it's not two neutron stars, but maybe a neutron star by dwarf. But this is sort of a small numbers game that is starting to grow. And during Kostov's thesis in the last couple of years, it turns out there's actually, if you plot ejector mass on the x-axis and nickel mass on the y-axis, and you plot the ZTF sample of events, then of course we all know and have studied stripped envelope supernovae for many years. But there is now, pieces of this phase space which are occupied by what you could call strongly stripped supernovae, which sort of bridge the gap between the ultra-stripped supernovae and the regular stripped envelope. You could call it whatever you want, right? I'm sure there's better probably Swedish words for this. I think superluminous supernovae on the Swedish version of this plot was hellish supernovae or something. I don't know what that was. Okay, but the strongly stripped and ultra-stripped supernovae, and very recently Costa published Supernova 2023 ZAW, which is an ultra-stripped supernova. It's not actually as stripped as IPTA 14GQR, but there are two components to the emission. There's a shock cooling component, and then there's a nickel component, and the nickel component has just nothing. It's the bottom most point that you can see on that plot there, right? There's absolutely very, very tiny amounts of nickel in this event. And Supernova 2023 ZAW is also possibly coming from a low mass progenitor in terms of the massive star, and also possibly giving us the opportunity to go and look for the neutron star if a neutron star was indeed created, because it's very, very close to home here. So there's been some good progress in trying to understand that penultimate step, right? That step just before forming that compact neutron star binary, by looking for a supernova that has exceptional amounts of stripping. And if you go two steps before, right, you want to actually look at common envelope evolution, right? So you want to try to understand common envelope physics, where you have two stars in a common envelope. The viscous drag forces are such that you are able to reduce that orbit size to extremely compact. So another one of my students, Viraj Karambelkar, has been looking at ZTF data to systematically identify what we call luminous red novae, because they're more luminous than novae and they're red, right? Completely phenomenological name. But this class of events has been associated with common envelope ejections. We don't know whether it actually leads to a merger or not after the ejection. I think that remains an open question. But with ZTF, Viraj was able to build so systematic a sample of these luminous red novae that you can actually plot them up now as a sample on a rate plot, which is rate versus absolute magnitude, right? So you saw versions of this plot in Dan Perley's for a talk yesterday on supernovae. Now you can do this for a class as rare as luminous red novae. And what Viraj is finding is that if you take the 3 events in our galaxy, which is what Chris Kochanik did in 2014, that's the green line there, that follows a very different slope than the blue line, which is the ZTF events, which are much more massive stellar mergers in galaxies far, far away, right? Now, it's a bit of a broken power law. We actually are missing what's in the middle because we don't, we can't find things that are -10, -11 absolute magnitude with ZTF yet. And they might also be extremely red, right? So to finish the job on the shape of this luminosity function, which is actually consistent with BPS models from Howitt et al. And actually consistent with rates with the large error bars of compact binary mergers. The part that is still an open question is, are we missing some luminous red novae in the gap between the green line and the blue line there? And that's because these are inherently extremely red, extremely dusty events. If you look at any light curve, okay, the blue emission fades very quickly, the red emission lasts for a very long time. And in fact, you expect theoretically in work done by Morgan McLeod and collaborators that there's a very, very large amount of extinction here. In the last few minutes here, I'd like to take a moment and talk about some of these infrared projects. By the way, we have confirmation these are indeed luminous red novae with some JWST spectra. But in the last few minutes here, I want to take the time to talk about some of our infrared surveys, because infrared has 2 things that are very powerful, relevant to this talk. One is infrared can overcome self-obscuration. So it's very good to study things like stellar mergers and common envelope events. And it's really good for overcoming bound opacity. I say right now that maybe these neutron star mergers are too rare, or maybe they're too faint to find with ZTF, but they could also just be too red. It might be that we got very lucky with GW17 or 817 with this bright blue emission that made it super easy to find by multiple people within minutes of each other. In the case of future events, the guaranteed emission is the emission that is powered by bound opacity that has opacities of 10 centimeters square per gram instead of 1 centimeter square per gram. So the bulk of the emission may actually be in the infrared. So we need to sharpen our infrared toolkit. So going back to this beautiful picture of Palomar, there are these 2 tiny telescopes here, Palomar Gatini-IR, it's 30 centimeters with a 25 square degree J-band camera, and Winter, which is a 1 meter telescope with a 1.2 square degree in-gas camera. Both of these, Gatini-IR has been running since 2018, and Winter has been running since earlier this year. Both are in survey operations mode. And what we are starting to do now is look for the infrared emission from kilonovae with Winter. Now, Winter is not as cold as I would like, but that's a story for another day. But the point of building wide field infrared surveyors is to go and look for infrared emission from kilonovae directly. This here is a picture of the telescope and the camera from Winter. And here are just a series of GCNs from Winter. And looking ahead, since we have Saul in the room, big shout out to Saul for enabling the Roman Space Telescope, which we heard yesterday at dinner started from SNAP. What I've been doing in this context is that I've been working with the IPAC team to take the ZTF pipeline and take it to the next level by applying it to the Roman Space Telescope data. So we have a project infrastructure team called RAPID, where we will be taking every single image from Roman, subtracting it and putting out alerts for the entire community in real time. We'll also do the usual light curves and post-photometry service and all that good stuff. So infrared time domain is something that I think has a lot of potential, especially over the next few years. Now Roman is a quarter square degree. It's wide field, but it's not very wide field. It's not quite above a square degree. So if you ask me what is my dream machine in the infrared, then I'll take the last 2 minutes here to share that dream with you. And that dream is to take a 1 meter telescope, not even a Schmidt telescope, but we actually have this really cool double meniscus design where you can get a very fast beam with very, very high optical quality, very high Stroll ratios for 50 square degree field in the infrared, okay? And we do this, there are two major problems in the infrared. One is the night sky is really bright, but what you can do is you can go to Antarctica, which is almost as good as going into space because the night sky background in K-dark is a factor of 40 lower. The second problem is the detectors are really expensive, but then we have a cool trick there where we can take regular good old silicon wafers, the same silicon wafers we use for ZTF, and put a coating on the indium bumps with molecular beam epitaxy to get quantum efficiency in the infrared. So these two tricks actually work, and the two big, sort of technology risks here. Then we have what we need to build this extremely powerful surveyor called Cryoscope, which is a fully cryogenic telescope in the infrared. Cryoscope would have a volumetric mapping survey speed, which is 5 times that of Roman, and in fact 1.4 times that of Rubin in the Y band. And this is a very small, very modest project compared to our flagship projects of Rubin and Roman, right? I mean, fewer zeros in the budget, okay? The fun thing is actually I have a graduate student who dreams this dream and is in the lab and starting to test these new optics, and we are actually putting together a prototype, a quarter-scale prototype, and the French-Italian polar agency IPEV has given us permission to go test this on sky. Nothing is more helpful than actually an on-sky test, especially when you're trying some very new technologies that have not been, they look really good in the lab. Look at those Stroll ratios, right? But I'll believe it when there's stars here. So we are going to go, and we have a boat on October 28th that we need to catch to test this new technology. Can we weather the weather? I don't know. It's pretty cold there. So that's one of the big things to learn is how do you survive in extremely, extremely cold weather. The electronics, I mean, not just me, but the electronics has to survive. I'm not so important, but the telescope is, okay. All right, so with that, I'd like to summarize. ZTF, if you're interested, please talk to us. We are looking for new partners. Kilonova, please be patient. Nial will tell you about some fun kilonova, probably hopefully from other events, but as far as neutron star mergers go, patience is the most important word. Infrared, I think there's some fun things happening. So please stay tuned for some very cold Antarctic fun. And with that, I'm happy to take questions.
Thank you so much, Mansi. Questions? Yes, Thomas was first.
Thank you for your super interesting talk. I have 2 questions. The one concerns what you showed with the nickel masses and the ejector masses. Do you have a similar compilation of data for the explosion energies?
Costa, do you?
Yeah. Could we see it?
I'm happy to talk to you.
Okay, thank you.
Okay, please show it to Thomas in the next coffee break.
And my next question would be on the simulation you showed by, you said, I think, Ehud Nakar, right? Mm-hmm. Maybe he can just quickly tell us how he launched this jet, how the parameterization worked, what was the energy injection time and energy?
Yeah. We put it by hand.
But I would like to know the numbers.
It's different from different simulations, but the one that actually fits the data at the end were launched for about a second, opening angle of 2, 3, 4 degrees, and total energy of about 10 to the 50 ergs, and isotropic equivalent 10 to the 52.
With some delay compared to the plunge to the merger?
Yeah. So there was, in order to get the shock breakout, we needed a delay of about half a second.
Because we had similar simulations self-consistently from Oliver Just, where we also had these, let me say, inefficient jets, which didn't really break out relativistically. I don't know whether the parameters match somehow, but you could be guided also by some models which we had out in the literature. Thanks.
Yes, Adam.
Very nice talk, Mansi. I appreciated your comment about being patient, but many of us are not so patient. So how do we understand or get our head around 2017 event, and year after year I hear gravitational wave talks, and I kind of can't believe there hasn't been another event. So I guess my question is, can you give us some perspective between the follow-ups you've done, the independent searches you've done with ZTF, the phase space, the volume? Are we overdue, or are we going to end up saying 2017 event was like the 5 sigma event? How do we understand these things?
I hope it's not the 87A of my life. But yeah, let me give you a couple of answers to that, Adam. The first one is, if you think about neutron star mergers, then there has only been one other neutron star merger that LIGO has reported, which is GW190425. And unfortunately, that was a single detector localization. So we searched whatever piece of that 10,000 square degree localization we could access that was not blocked by the sun, but chances are it was likely where the sun was. So there was half of it that was just not accessible to anybody, right? So ZTF mapped that area but didn't find anything. So that was the only chance that LIGO gave us for looking for another binary neutron star merger event. Now with neutron star black hole merger events, there have been a few more chances. There have been 4 chances, I would say, to look for a counterpart. But there the physics is more complicated. So if you see this figure here, then whether or not you get electromagnetic emission depends on the spin of the black hole, the tidal deformability, the mass ratio. There are many scenarios in which the neutron star could just get completely swallowed whole by the black hole, right? So, and in fact, in a couple of cases, that mass ratio was very extreme. So even though we went and looked, there was no real chance of actually finding a counterpart because 99% confidence, just fell directly into the black hole. So I think we need nature to cooperate a little bit. What we are learning is that the rates are lower or these events are much redder, right? So I think first we need a few more events. And the independent searches, when we started, the LIGO rates were at 3,000 per gigaparsec cube per year. Our independent rates are already below 900. And I think now actually the latest number is below 700 per gigaparsec cube per year. Their bottom lower limit is 50. Right, so they started with 50 to 3,000 per gigaparsec cube. So we're just learning that the rates are actually on the lower end. That's just how this goes. So I think that's where the patience is necessary. But my sense is that O4B is going well. I think we could get one more event. I'm an optimist within the 12 more months of O4B. And by the end of the decade, I think we'll be at few events. Yeah, I think 10 would be very optimistic, but few events. So I think it's a slow roll, but I think only people who are in it for the long haul will reap the fruit here. There definitely are people who are getting frustrated. 170817 was just such easy pickings. It was in our backyard. It was so bright and blue. It was so easy to find 17th mag. We had way too much fun with that one.
Let's see, I think Sol first. Yeah.
So as an experimentalist, I have to pick up on your final topic, which was, I'm curious, what is the story about this capability of adding a coating that gets you infrared capability? Can you say a little more about what we get out of that?
Yeah, thank you for asking. So Raytheon, which is an industry partner, they are taking silicon wafers, and on the indium bumps on the silicon wafers, they are putting in, adding molecular beam epitaxy. So they're just adding this thin layer on top of the silicon wafer, and we are measuring in the lab quantum efficiencies of 95% at 2.4 micron. Otherwise, silicon has a band gap at 1 micron, right? So it's hopeless. You get 0 photons beyond 1 micron. But with this trick of adding this layer, we can get wafer scale devices now which beat the cost curve by a factor of 5 per pixel. And I want a 50 square degree infrared camera, so to be able to afford that focal plane, I need the cost barrier to be broken.
Are they able to keep the noise anywhere near the teledyne kind of noise levels?
Yeah, so noise is currently entirely dominated by sky. And the sky is much darker in the Antarctic. So the read and dark current are quite low in the lab. But again, I want to see it on sky to believe it, right? I mean, in the lab, it looks very promising, but that's why we're doing this prototyping exercise right now, where we, for the next 2 years, we will be taking different pieces of the prototype to Antarctica to test things and retire the technology just before we go for the full dream.
Oh, that's great. Is there anything written yet on it?
I can send you our SPI proceedings. My student is in Japan presenting. So yeah, we have SPI proceedings right now.
Okay. And
Okay. I also have a question about the Antarctic IR. So there is a good chance that the next galactic supernova will be
Yes.
in this direction, and it will be only observed at least early times with IR.
Mm-hmm.
So are you ready?
Absolutely. I have been ready since 2018 because, where is Kishale? Here he is, okay. So we built Palomar Cattini IR, which is a 30 centimeter telescope with just one little 2K by 2K detector, but it has a whopping 25 square degree field. And with that, we're already monitoring the 3 pi of the northern sky every 3 nights. So we are, and in fact, for 200 red giants that the neutrino community says, okay, one of these is the one that's going to explode as a supernova. They have a list. They literally have a hit list of these are the most likely red giants that are going to explode. We're actually reading them out at very high time resolution so that we can catch any change in the activity of the star before it explodes. So if it is in the south, I need another friend in the south who's going to put a telescope there. I mean, I have this idea of the DREAMS project, which I'm trying to convince the Australians. They haven't yet gotten on sky. But we are going to make sure that even before Cryoscope it comes online, we have coverage in the north and the south to not miss an infrared photons from a galactic supernova.
So you're connected to the stream from the neutrino detectors because you will have a few hours.
Yeah. I'm tuned into SNEWS 2.0, I think now, 2 point something else it is.
okay, final question, Selma. And then we'll
Thank you for the very nice overview. The things I would like to ask, but about the April event. So there's not a detection. I don't know why I asked anything sensitive, but is the chance that it's real overestimated, or was there an event that was not recognized? Is it too far, or didn't give it any light? I think that's the 4 options. Is there any favorite of these that is coming?
Excellent question, right? So it was not too far. It was only 200 megaparsec away, right? So we are very sensitive to a counterpart. Now we don't know these parameters. So we don't know the spin of the black hole, we don't know the tidal deformability, and we don't know the mass ratio. Those are proprietary to LIGO. But the LIGO gives us this one parameter called Has remnant, which suggests that it was not too bad on this plot. Now the sensitivity is that LIGO puts out these triggers in real time, not with their full analysis. So they always tell us, okay, don't hold your breath till we finish our full analysis. It may take us 2 years, but they will do a full analysis and they may revise their estimates, and that's when they'll publish all these parameters and models. So we are confident we didn't see it. Maybe you
the
found
galactic plane as well, of course, which presumably was at least made some part of that error region quite tough.
Right. So it's possible that it was extincted due to the galactic plane, right? So if you look at the limits, but what we did to try to overcome that was look with red filters, with DECAM in particular. So the reddest filters from DECAM are not as good as infrared, but at least overcome some of that galactic extinction, which was pesky in this case. So due diligence is done, and the exact parameters in physics to constrain, okay, this means that the neutrons are black hole kilonova, should have ejector mass less than this, or we can't do that until more parameters are released, which may take a little bit of time. And the significance may get revised is what we are told to mentally prepare for, because in 03 they did this to us a lot, right? They would release these triggers and then they would even retract them like 2 years later. It was like, okay, please don't retract. Don't tell us things that you're going to retract later. But it's a game we learn.
As we this way than the other way around.
Yeah.
Yes, very quick question from Smaranika while Nial gets set up.
Yeah, thanks for the very nice talk. So I was curious that now you have multiple IR instruments this coming up and stuff. So I was curious that how the joint work of probably ZTF and this winter and your DREAMS project, how will that increase the IR community's rate of detection?
Fantastic question, right? And in fact, Sam's PhD thesis here is how do you combine ZTF and winter effectively? So she's looking at the reddest transients from ZTF and triggering winter. But I think actually the combination of different surveys is the wave of the next few years, right? I mean, that is doing things that no one survey can do alone, but combining surveys with joint queries, with asking the right questions. What types of discoveries does that enable that we missed before is going to be what will yield some, I think, fun discoveries in the next few years. It's right here already, right? This era of combining the different discovery streams to make discoveries, new things, to find new things, find the reddest things, maybe the bluest things when Ultrasat is launched and Avisha is smiling. Yeah.
Okay, well, let's thank Mansi again. And our next speaker before the coffee break is Nial Tanvir, who will tell us about electromagnetic signals of compact binary mergers. So we continue a little bit in the same vein. Please go ahead.
Thank you very much. I apologize for my slightly croaky voice. I'm hoping I'll get through the whole talk without it breaking down. I'm talking about electromagnetic signals from compact binary mergers. Mansi has already discussed some of those aspects, and indeed it's been touched on also by some previous speakers. I guess I'm going to take quite a sort of observational, empirical kind of view, partly because we have some theory talks coming up later, which I guess are going to address some of those issues. At the top there, I've got a few of my kind of big collaborations that I'm part of, although this talk isn't particularly presenting results from any one of those collaborations especially, but I thought I'd flag those up. Okay, well, so what are we talking about? Obviously, as we all know, compact binaries, neutron stars or stellar mass black holes, if they're in a tight orbit, they'll merge within a Hubble time. So that's well known due to gravitational wave losses. And of course, if one of the components is a neutron star, then there's a good chance of getting some kind of electromagnetic signal. If they're both black holes, I think there's a lot less chance, but people still think about that. And that, of course, in addition to the gravitational wave chirp, makes them especially topical and interesting in the present era. Since we're talking about large surveys, I thought it was worth commenting that the gamma ray detections in particular that I'm going to be talking about, so you'll probably guess I'll have a bit of a GRB bias to this talk. The gamma ray detectors that we have are intrinsically very wide field, and so although we're not talking maybe about the same sorts of numbers of transients as you might be dealing with if you're discussing, for instance, ZTF, we are talking about large volumes of the universe that we're effectively surveying for transients with particularly in the high energy and increasing in the future with the gravitational waves as well. So why are we interested in doing all this? I don't really need to explain this, I'm sure, to this audience, but just for completeness, we'll have a run through and remind ourselves. So, of course, the electromagnetic counterpart, if you identify it, gives a very precise localization, particularly if it's optical infrared. And hence, it's the route to finding host galaxies, environments, redshifts, crucially. That then further enables tests, for instance, of fundamental physics, cosmological tests, for instance, the use of standard sirens to obtain the estimates of the Hubble constant. By finding the environment, it gives us the links that we would like to massive star formation and formation channels of these kinds of binaries. And then, of course, very importantly, the role in nucleosynthesis, heavy element nucleosynthesis, that we all hope we'll have a much better understanding of when we finally ultimately can write down the whole budget of our process production in that's due to compact binary mergers. So this kind of meeting, it's always nice to dig back a little into the Stone Age, as Mansi called it, and so I thought we should remind ourselves as to the first discussions of electromagnetic radiation from binary mergers, and I think that probably goes back to papers like this, famously the Eichler paper from '89, and this paper here, Moshkovich, from '93, where they discuss the possibility, particularly in the context of at least some gamma ray bursts being produced by compact binary mergers. One had this speculation that gamma ray bursts might be cosmological, and so you needed a very large energy reservoir, and of course that's something that naturally enough arises in compact binary mergers. The details of these models, I think, don't correspond very well to our modern understanding of gamma ray bursts through ultra-relativistic jets, but the notion, at least, was planted in these ancient and venerable works. So what is our modern understanding? Again, thinking now from the starting off from the high energy point of view, of course, we now know that gamma ray bursts come in two classes, at least, discussed. And so we have the long duration class, as mentioned yesterday, primarily, we think, from core collapse of massive stars and so-called collapsars, although that's something that I'm going to be coming back to, exactly what level of contamination there is between these groups, and the short duration class, which are the ones that we now commonly associate with compact binary mergers. And some of the evidence for that we got early on in the Swift era from the first good localizations of short GRBs is well illustrated by this very first one. So you look at this, it's only got an X-ray localization. Faint afterglows for these short bursts means we often don't obtain optical observations of the afterglow, detections of the afterglow. And that obviously means that the localization is that much poorer, and our confidence in the host galaxy is that much worse. In this instance, the fact that the X-ray localization was sitting right next to an giant elliptical galaxy at fairly low redshift was immediately suggestive of a different progenitor channel here, that most likely this was the host. The chances of such an alignment, if they were unrelated, were pretty slim. And so this looks as if it's the host galaxy. It also looks as if the transient is offset from the host galaxy. And both these things are consistent with a compact binary origin because it doesn't require a massive star progenitor. And also the binary might be kicked for some long distance outside its host galaxy before it finally merges. And so there was a consistency argument there, whereas it's inconsistent with a massive star origin, unless it turns out that this association really was just chance, and that really one of these other little fluffy background galaxies, in fact, was the origin, the host after all. So we still don't know, but this was the kind of evidence that you build up statistically over time to suggest that the short bursts are primarily, at least, compact binary mergers. The situation improved, I would say, in 2013, where we got, and for several years, people had been looking for kilonova signatures associated with short GRBs. Difficult, because, of course, the afterglow itself is bright, but typically what we'd been doing was looking in the optical for a relatively short kilonova in the optical, and only with the advent of the Kaysen et al. Study in 2013 did we sort of realize that that strategy probably wasn't optimal, that we should be looking on somewhat longer time scales of more like a week for an infrared excess. And so that's what we did for the first time in mid-2013. And we got this one single point. So 1 point, isn't necessarily ideal, but it certainly seemed to show that we had infrared emission well in excess of what was predicted from the afterglow at around about a week in the rest frame post burst. And so that was, at least we argued, a very good candidate to be a kilonova associated with that event. Wind the clock on, and I won't belabor this point because you've all seen it too many times, but of course famously the 1708-17 case came along. The kilonova behaved in many respects just as expected, although obviously a rather brighter, bluer optical flash at the beginning, suggestive of multiple components of ejector and multiple components of emission. And so this was the sequence, the movie that we put together based on the VISTA imaging at the time. So my modelling efforts are not quite up to the ones of Udi. but this is what you can do with PowerPoint. And actually, this is pretty damn tough with PowerPoint, let me tell you. So I like to take some credit for it. Anyway, it looks like that. So I'm not going to discuss the actual theory stuff, as I say other people will, but we will discuss this jet, and so it's of particular interest. Again, famously for 1708-17, because we were observing off the jet axis by some 20-odd degrees, we believe, the afterglow itself didn't become visible for some time after the burst. But when it did, it presented us with another firework display. We observed all the way from radio to X-rays, this rising off-axis afterglow, and that can be understood, again, perhaps for the students in the room, maybe, in terms of the expectations of relativistic beaming. If you have this fairly narrow jet, I should point at the screen, fairly narrow jet initially going at very high velocity, then the relativistic beaming will project essentially all the radiation forward, and you'll miss it as you observe from some off-axis angle. But as that jet front's emission front slows down, the beaming cone widens up and gradually it comes into your field of view, and so the afterglow rises up instead of simply declining. But then once it's fully in your field of view, the behavior then becomes just like the standard afterglow behavior, and it begins to decline as a power law is at least the expectation. And that's what we've seen now going on many years. And so even now there is a very marginal X-ray detection with Chandra quite recently, which is now obviously quite a few years after after the event, and it's starting to drop out of the detectability in radio and did some time ago in optical. There have been other kilonova candidates observed accompanying short duration gamma ray bursts, and so this is a fruitful route to studying kilonova even in the absence of gravitational wave detections. And this one is, I think, the best so far, 1608-21b. I actually announced a preliminary result last time I was in Stockholm on this particular event. Subsequently, we did a lot more careful modeling, and I'm not going to try and explain all these elaborately colored lines, but the bottom line is it was consistent with a kilonova, inconsistent with just afterglow behavior, but a rather fainter kilonova, probably an ejector mass, something like 1% of a solar mass in this case. There are others. Of course, we have a back catalogue now of short GRBs going back many years, so one can look in some of those and say what were the limits on, at the time, any afterglow emission was what we thought we were looking for, but we can say, okay, those are also, in some cases, meaningful limits on kilonova emission. And again, this isn't necessarily the easiest set of figures to follow, but bottom line is there are some, in this case, some upper limits here on emission which are below where you'd predict a GFO-like kilonova to be. And so this is telling us here that any kind of kilonova emission in this case, and also in this case, must be fainter than GFO by a couple of magnitudes or so. However, there have been some other more recent developments which I think are very interesting in a number of respects and sort of pertain to some of the questions that we've been discussing already this morning. And the big surprise came in 2021 when we obtained, we had this alert for this particular GRB. It looks like a long duration GRB, and so naturally one thinks that this is going to be a collapsar. In terms of the hardness duration plot, which we saw earlier on, you can see it's at the firmly in the long and soft GRB class there. However, in terms of its position on the sky, it was again curiously close by to a low redshift galaxy. So this could, of course, have just been chance, but we took the risk of doing some further follow-up, and we found evidence, in fact, of kilonova emission associated with this apparently long duration burst. At a distance, you notice, of only 350 megaparsecs. So starting to be at the, the sticky end of the range to which the current LIGO detectors might have detected something, at least sub-threshold, if of course they'd been turned on, which they weren't. The evidence for the kilonova again is illustrated by these not so easy to interpret coloured lines, but again pretty pretty consistent with a regulation kind of kilonova. Even more surprising then, last year in March we had another long GRB. This one turned out to be one of the brightest GRBs that had ever been seen. And so immediately that's very exciting. The problem with it was very far south. It was difficult, in fact, to observe, and it took us some time to even narrow down the localization. But we were excited because it stood out, this particular event, it's the green point here, stood out particularly on this plot here, which shows basically the prompt fluence, the initial gamma ray flash was, as I promised you, very bright, one of the brightest that's ever been seen, certainly by Fermi, against the afterglow X-ray luminosity, which was not anything to write home about, pretty average. So a strange kind of event, and one that, again, demanded some follow-up, even though that turned out, as I say, to be difficult. But eventually, we did find this counterpart, which again seemed to evolve and seemed to become red. Now, over a period of about a week and a half, so it was all getting rather tricky, but we thought we had enough evidence here that this could be another example of one of these apparently long duration GRBs associated with a merger in potentially a relatively low redshift galaxy. So the potential host in this case is this guy over here. Oh no, sorry. Yes, that's right. In this image, this guy over here. Not a very pretty picture, but that's what we were having to deal with. And this was good enough to convince the STF SNIa director to give us DDT time to do some spectroscopy of this candidate, and you can see the JWST image of the host galaxy is a whole lot better than the one that we had from the ground. So a beautiful thing here, and this was the counterpart. So again, is only consistent with a binary merger if there has been a large kick and a long time to merger. But we're used to seeing that in the short GRB population, so seems plausible. And so what we found was very exciting. We got this beautiful James Webb spectrum here with NIRSpec. And it was very puzzling for a period of time because there were, and it's not shown in this figure, they've been sort of excised, but there were lines, emission lines within this spectrum corresponding to redshift 3.9. Now, that would have been interesting. It would have been interesting because it would have made this the most luminous GRB intrinsically by some orders of magnitude. And so we never really thought that that was possible. And we now think that basically it was slightly offset. And essentially, this is just a background galaxy that happened to lie in the slit. And so if we ignore those lines, what we're left with is a rather, typical sort of not highly featured spectrum, but with this one clear emission component here, which we speculate at least may be due to our process produced tellurium 3 feature there, although people discuss other possible origins. Okay, so that's been the interesting activity. Again, I suppose worth commenting that the distance was sort of at the sticky end of the LIGO range if the detectors had been turned on, but again, unfortunately, they weren't. One could then go back and ask, I already showed you some cases where there were upper limits in terms of possible kilonova emission associated with short GRBs. We can also ask now, what about long GRBs, and in particular, some of the historical long GRBs for which people had ruled out the existence of a an accompanying supernova to any great or to very deep limits. And so this was a famous one, 060614. The light curve is shown here in the black points. Various possible supernovae are shown there in the colored points, and you can see that it's obviously wildly inconsistent with the existence of a supernova. Again, it's a sort of longish but possibly short sort of burst. It has a short, sharp spike at the beginning, and then a long extended emission. So this had been a sort of controversial event for a long time, and it had already been suggested that maybe this one point, again, essentially this one point here at a couple of weeks or so after the GRB might be in excess of the afterglow. It looks very clearly in excess in this figure, but of course, exactly where you decide to put the afterglow is, has a certain degree of slop in it, and so it's still not clear if we're seeing, if this is due to a kilonova, as the authors here claimed, then it's rather surprising to see it in the I band at 2 weeks, but maybe that could be understood if there's some, for instance, some extra powering of emission from, say, a magnetar remnant or something like that. So I think this is certainly interesting and suggestive, but not conclusive. Let's just take a step back then to GFO, and it's important to think about what else we learnt from that one spectacular example. So I'm not going to dwell on this at any length, but the spectroscopy itself that we obtained, particularly the sequence obtained with VLT X-shooter, is very rich. It covers a broad wavelength range of the optical and near infrared. It shows many bumps and wiggles, which certainly cry out for explanation. I have to say I was a sort of pessimist when we first obtained these spectra. My feeling was that the velocities were too large, the features were too broad and too many possibilities, that it might be very hard to decode them. I think the progress has been faster than I was expecting. Already, Watson et al. In 2019 put these very prominent features around 1 micron. They explained those in terms of strontium-2 evolving. There were deep limits as well, interesting limits on the existence of platinum or gold, which of course is the question that the journalists always ask if you're trying to sell this work to them on the basis that it's these kilonova are producing all this platinum and gold. They want to know if we've seen it. No, we haven't. However, I think progress continues, and in particular, again, the group in Copenhagen have been responsible for a good deal of that. And this very interesting paper recently by Albert Sneppen, a PhD student in Copenhagen, who's written several papers now, increasingly detailed analysis on these GFO spectra, putting this all together and explaining several of these features, taking account, it turns out importantly, of the light travel time differences between different parts of the kilonova, and that helps you understand the evolution of some of these features, including this one here that we saw only in the HST data, spectra around 1.4 microns, which may be explicable as being due to lanthanum-3. Well, okay, so that's the story from the GRB point of view. The question has been raised: where are we in terms of the gravitational waves? Mansi already sort of quoted some constraints on volumetric rates. I'm not going to give you any precise constraints, but I suppose my sort of pessimistic reading of the runes is that maybe we're down here at a volumetric rate of, let's say, some tens to 100 or so per cubic gigaparsec per year. I think that's certainly the absence of very many triggers in O3 and O4A is certainly pushing us down in that direction. To be honest, from the short GRB volumetric rate, of course you don't know the exact mapping between the two, these sorts of numbers don't seem outrageous to me. but you know, they're certainly making life difficult for us. It's interesting to compare this to this famous paper by Still Finney, again back in the early 1990s, and I noted that he had an ultra-conservative estimate just from looking at populations of compact binaries within the Milky Way of 3 per year per cubic gigaparsec, or within 1 gigaparsec. So I suppose that's a slightly larger volume. So we're at least above that, but maybe we're sort of not. You know, we're not. His conservative estimate is something we're pushing down on. So I think it is definitely the case that we were very lucky with 170817. Thank you. It could be that this was, you know, a 1 in 10 year sort of event at this distance. It could be possibly even a 1 in a century event at this distance. I think, on the other hand, we've been unlucky because we did have those 2 long bursts, as I emphasize, which seem to have been associated with compact binary mergers, which might have been detected had the gravitational wave detectors been on at the time. And so I think that's certainly unfortunate. You'll appreciate the fact that I told you that at least one of those was the second brightest GRB we've ever seen, but, you know, we were also lucky there in a sense. So, you know, we can't expect to be seeing one of those every year. What's going to happen in the near future that might affect us in the gamma ray side? So in 1 week's time or 8 days' time, we should see the launch of SVOM. So this is a Chinese-French-led mission, essentially similar to Swift. So if you're familiar with Swift, you'll have the idea of how it works. It does have some advantages over Swift, one being it's sensitive to rather softer energy triggers, but it does have high energy gamma ray detectors on as well, higher energy as well. So it has a broader high energy spectral coverage than Swift. It has a visual telescope on board. So for more GRBs, it should find optical sub-arcsecond counterparts, and I think that might also be helpful for gravitational wave follow-up if we're lucky enough to get high energy emission again from a gravitational wave event that's within the field of view. The localization will immediately be considerably better, I think. And as was also mentioned, we also have Einstein probe already observing, still in a commissioning phase, but giving very wide area soft X-ray monitoring of the sky and finding many different classes of event, and that also could be very useful to us going forward. I don't think I'll dwell on this one too much. The Vera Rubin has already been mentioned. It could well be the way, our best way perhaps of localizing the optical counterparts of gravitational wave events in, let's say, the next GW observing run, probably not going to be ready in time to help out in 04, but let's say 05 and onwards, Vera Rubin could certainly be the route for us to explore that parameter space most thoroughly that Mansi was discussing. I wanted to talk about the ELT a little bit. I think going forward, if we want to obtain beautiful follow-up of kilonovae, either associated with gravitational wave events or GRBs at rather higher distances, we're going to need more powerful telescopes, and the 30-meter class telescopes like the ELT here is certainly going to provide us with that kind of power and capability from roughly the end of this decade. I'm assured by Google that this is a famous building in Gothenburg, so if you're familiar with this building, then I hope you'll be impressed by the sheer size of the ELT, which is gigantic. And it's also coming along. So this is a picture from last week, and you can see that the superstructure is now essentially completed. Not the gigantic shutters, they're still to come, but they're starting to actually wrap the outer part of the dome there. So the dome itself is going to be completed fairly soon, and look very much more complete by the end of this year. Still then going to be another 5 years or 4 or 5 years to complete the telescopes and to install the first light instruments. But anyway, watch this space. It's going to be super interesting. Looking forward further into the future, I wanted to discuss really what we're going to do for observing the counterparts of compact binary mergers in the late 2030s. A young man like myself has to always be looking forward to these kinds of opportunities, even if they seem rather far away. And so I'm particularly excited by this mission that we have been, thank you, that we've been pushing now for seems like many years, at least 10 years with ESA. We've got very far through the process, but we're still not actually been selected for launch, but we're still in the game. And so any of you that are influential within the ESA system, I hope you'll also be excited by this proposal. Essentially, Theseus is going to be like a super Swift, that much more powerful, that much more broad energy coverage in every respect, and also carrying a comparatively large infrared telescope as well, particularly suitable for following up high redshift events and also kilonovae and lower redshift events. So why is that exciting in terms of the compact binary mergers? The answer is that hopefully Theseus may eventually be flying in the same era as the third generation gravitational wave detectors. And so you've probably seen this figure before showing that we can detect with something like Einstein Telescope or Cosmic Explorer compact binary mergers involving neutron stars way out to high redshifts. And so covering essentially the whole of cosmic history. That means the numbers that we'll be dealing with are vast, so hundreds of thousands of triggers over the per year even. But of course, most of those are not going to be pointing any kind of jet at us. And so most of them are going to be far away. So the kilonova observations may be really tough, but the ones at least that are pointing a jet at us, the fraction that are, there's a chance of seeing the high energy emission, therefore getting immediately then a very refined localization and giving you a best chance at least of exploring the associated kilonova. And so a mission like Theseus has that wide field high energy coverage that allows you to see at least those aligned sources, and the kind of numbers that we're talking about are not huge, not when you've been talking about 100,000 triggers, but they're certainly interesting, many tens of events per year, and so over the course of a mission you could build up significant samples this way, and it's probably really the way of continuing this or exploiting the multi-messenger science that's opened up by the third generation gravitational wave detectors in the 2030s. Okay, so just finishing off then, compact binary involving neutron stars can produce, as we've discussed, a rich variety of electromagnetic signals. I've not actually touched on all of the possible signals that one might see. I've not discussed, for instance, later time emission as the kilonova ejector begins to interact with the external medium. The range of gamma ray bursts we now understand. There's a slide missing. I realise I'm annoyed. What happened to that slide? I must have deleted it at some point when trying to remove what I thought was unneeded slides. Okay, so I'll just give you verbally the range of GRBs that we now believe accompany compact binary mergers seems to be broader, at least a fairly significant number of long GRBs, certainly at low redshift, may turn out to be compact binary mergers. The slide that's missing tried to sort of quantify that a bit, And what we've done recently is basically look at all of the low redshift GRBs that we know about and kind of put them in bins of either definitely a collapsar, definitely a short GRB, and therefore highly likely to be a compact merger. Ones for which there was no supernova seen, and therefore quite likely one of these long mergers, not 100% sure. And we're getting up to 30-40% of low redshift GRBs that could be therefore in this not in the long merger class, but in the compact binary class. And roughly split 50-50 between ones that give rise to short GRBs and ones that give rise to long GRBs. So at low redshifts, I think the sort of contamination, if you want to call it that, is potentially quite significant. Probably not dominant, but quite significant. As we've said, the rates of either BNS or NSBH in 03 and 04 so far is low, confirming a relatively low volumetric rate density. But we're hopeful that 04 will be extended further, giving us some better chances of getting some nicely localized events to follow up, and hope, of course, springs eternal for those of us in the long run. New facilities are already making an impact. JWST, of course, SVOM, an Einstein probe just beginning, Vera Rubin, and ELT as we look further up along into the later part of this decade. And then in the long term, I think we do have to always think of the longer term missions like Theseus. Any large facility takes a long time to build. You can't suddenly decide that you need a high energy mission once you've got your 3G gravitational wave detectors going, because you'd then have a lead time of a decade or something before you could get it up there. And so it's clearly necessary, if we're going to have this joined up multi-messenger, multi-wavelength, multi-facility kind of science going on into the future, that we plan carefully and try and organize these things and recognize and value their synergies now. So I'll leave it at that.
Okay, questions for Nial. Ooh, oh my gosh, I think usually I was fastest. So.
Hi, I was curious about this binary merger that's very far outskirts of the galaxy, the nearby one that you showed. So I assume the reason there was interest in this object was because of the location and the bright flux. I'm wondering, do you think there are sources that if you saw the same thing on top of that galaxy, you would not get late time infrared follow-up and wouldn't even realize that there's infrared excess over there?
Yeah, it's a very, very reasonable question. And I think it's sort of not clear. There are some people who, and it's not a game that is well established, but there are also differences in the high energy and the X-ray emission, which already also looks suggestive of a non-standard event. And so in that sense, our sort of ears were already kind of pricked up by that as well. Now, I think it's something you can't firmly pin down, but one looks for those kind of clues as well, that this could be an interesting thing. And I think, of course, if it had been overlapping with a low redshift galaxy, that would also, then I think we would have chased that up anyway. That anything that's happening in such a nearby galaxy is going to be valuable, be it collapsar or not, because that would be one of the very closest. So we'd have certainly followed up. If it had exactly aligned with a by chance a more distant galaxy, then indeed I suppose there could well be a case that we wouldn't.
Costello.
I have a nice question. So we saw in Mansi's talk that a lot of this binary companions could end up in white dwarf neutron star systems. is it possible that they give rise to some of this GRBs or long-lasting GRBs at all?
Yes, so indeed that is a model that is being looked at for certainly particularly the 230307A case. So I think it's possible. Whether it's favoured or not, I don't get the sense that that it's sort of currently the favoured model, but at least people are investigating the expectations there.
Would they expect it to be long duration?
I think it more naturally gives you that sort of timescale. So otherwise, you're cooking up other possible explanations for the long timescale. So whether it's magnetars, of course, are usually typically what we throw in to the mix if you want to get some extra energy and extend the timescale. Could be some kind of fallback accretion as well. This has also been looked at. So it's definitely uncomfortable, the long time scale. It's not a time scale that one immediately associates with the compact merger itself.
Okay. I think it was Thomas.
Yeah, I had a similar question about this event of 21/12/11. I mean, there were arguments in the literature long ago that the white dwarf neutron star merger is unable to produce a gamma ray burst because of too low accretion rates, and also extreme fallback in neutron star mergers had been included on grounds of theoretical arguments. So these scenarios. But my question was essentially the connection to neutron star merger is not established because it didn't have a gravitational wave event, right?
Correct.
So it could be something else.
Yes.
Extremely strange collapse of a star, maybe with very rapid rotation, or a white dwarf collapse to a neutron star with a disk, something of that sort.
I think that's a fair point. It has to find itself in this unusual location out in the halo of the galaxy. So you can't you don't have complete freedom to cook up things. But I think it's a fair point.
Mm. And a historical remark, because I always got this comment when I gave talks about the first suggestions of gamma ray burst. The connection actually is claimed to be first stated by Sergei Blinikov.
Okay.
Always pointed this out to me that in the early 1980s
yes,
he had a paper on
I'm
that.
sure. Yeah, indeed. When one looks carefully at the history, it's always richer and more not that simple potted history that you present.
Ashish?
So concerning in the long duration mergers, you had an earlier slide where you had the 2-second vertical line, but clearly the distribution suggested that there was a way perhaps to make it a function. So the ones that you think are longer duration but could be from mergers, are they consistent with the lower set of points you had, or would they be higher up?
No, they're very right in the middle of the, surprisingly so. Mm. I'll just comment, since you discussed that diagram, we do have 1 or 2 cases now of collapsars, which are in that what look to be the short duration class. So, there is, as you'd expect from just visually looking at it, an overlap. I think the extent of the overlap is what's really surprised us.
Mansi?
Yeah, so sort of building on Thomas's question, right? I mean, I've of course read your papers with great interest, excellent papers. But the interpretation, the interpretation of, I mean, I get the interpretation of red light curves to our process nucleosynthesis to heavy elements being synthesized, right? The opacity stuff is robust. But then the connection back to the central engine, I think it really is helpful to have a little bit more of an open mind, right? In terms of, could there be a weird low luminosity collapsar, right? I mean, Dan Siegel and others have papers on collapsars producing heavy elements as well, but they don't all have to be -17. They could be a little bit lower luminosity. And
I'm completely by that. I think the location is awkward.
dwarfs, and there is.
Well,
there are these.
Yes, I have an open mind, certainly. I think probably most of us do, although, you have to sell some particular conclusion. I would say it's probably, that the simplest explanation is probably remains the binary merger now. Anything else is somehow more exotic in a way, but why not? Yes.
I don't know if it's the simplest because you have to make a long duration engine out of it.
You do.
Right?
You do. Yes, true.
There are some good ideas for that too, but I think they're just all ideas at this point. Right?
Yeah, fair enough.
Okay, if there are any lingering questions, let's bring them out to the coffee break. But first, let's thank the speakers. Now we will get the theorist perspective. So please go ahead.
Thanks. So first I would like to thank the organizer for inviting me and giving me a very modest task to talk about all the frontiers of transient science from a theorist perspective. But giving me only 35 minutes, I will go for that, okay? So I will show some frontiers and it will be my perspective. So it will be mostly things that I'm interested in. So I will talk about 3 different topics, science topics, pure science, and one which is a bit sociological. And so first I will talk about the role of engine and jets in regular supernovae, and we've heard about it yesterday. I will say a few more words today. I will talk about shock breakouts, only very general issues, and then a few words about the theory of TDEs. And I will end with a note on careful, how should we use automatic tools. So let's start with engines. So if we look at the supernovae, regular supernovae, not interacting, and this is the sequence that Avishai described yesterday. So we have the H-rich, 2 P's, 2 L's. We don't see any evidence for engine activity. If you look at the explosion mechanism, as we heard yesterday, the neutrino-driven mechanism is probably the most promising. There are other possibilities yet. If we look at the strict envelope supernovae, actually we have many signatures of asphericity, many different in the spectrum and in the polarimetry, and many different signatures. And there is a growing evidence for jet activity and for engine activity, and I will actually talk about this evidence shortly. Maybe the neutrino-driven mechanism works here for all, maybe for some. Maybe not, because it's not clear that you can make all this aspherical, and sometimes also the energy of these events is relatively high compared to what you expect. We don't know. Finally, you have the GRB-associated supernovae. Here we show there are jets, relativistic one, there are engines, and there are very energetic supernovae. Here's a neutrino-driven mechanism. Would not work. And so you can think about it as kind again of a sequence of an engine or a sequence of an explosion mechanism. So on the one side we have the type 2s, 2Ps. On the other side we have the broad line 1Cs with the GRBs. In the middle we don't know, and it's not clear exactly whether actually it's not necessarily a one sequence. It can depend on many things, but how to connect this. So I would focus on these, on the strict envelope regular ones, and show what our evidence we have for engine and for jets. So I think that these are two questions that will occupy theoreticians, also observers. They occupied this in the past, but I think there will be a progress in the coming decade. And here, early spectra mainly are very important and can give us can identify jets. Actually, it's signs of jets. So let's start with those long-lasting engine activity. Not necessarily jets; it's an engine. So it was mentioned yesterday that there seems to be some disagreement, which is becoming more and more evident in the recent years, between the energy that we see in the tail of how much nickel there is in this stripped envelope supernovae. All these supernovae, the light curve is assumed to be powered by nickel. So we look at the tail, we know how much nickel there is, and we look at the peak luminosity, and it seems that the peak luminosity is too bright. And all these work have shown that in a different ways. The first one, by Sharon and Kushner, was showing it in a way which is very similar to what I will show you that we did in our work, but they did it on a smaller sample. And all of them got to the conclusion that somehow there is not enough nickel to explain the observation. So what we did is we used a method which was also mentioned yesterday by Avishai, it's an extension of what we call the Katz integral. It was developed by Boaz Katz and collaborators in 2013. And the idea is simply to take all the quantities that you see, multiply it by the time, and integrate over the entire duration, the entire light curve. And what it basically gives you is an energy conservation which takes into account adiabatic losses. So this is an energy conservation equation. I will not get to the details of the exact equation, but basically, if we know
if we know this is the integral over the bolometric luminosity, and we know how much nickel we have in each event, and we know the nickel from the tail, we measure the tail, we can see how much nickel, then we can remove the contribution of the nickel from this integral, and what we remain with is contributions to this integral, to the luminosity integral multiplied by time over time. We get the contribution from non-nuclear power. And this non-nuclear power, we can think about two options if you have other options, or I can think about three options actually. If you have other options, you're welcome to suggest. One of them is what is called here ET. This is basically cooling envelope emission. Second is an engine. Look here. Second is an engine. And the third, which I do not show here, is interaction. Okay? So the method is the following. For supernova with good observations, we calculate the bolometric luminosity, we measure the nickel from the tail, we remove, and we expect it to remain with almost nothing. Because we knew that stripped envelope supernovae are mostly powered by nickel. And so we did it for 54 stripped envelope supernovae of all types. The result was published in Nature about a month ago. And so we measured the nickel. I just told you what we did, and this is the residual. So actually the residual that we have is very significant. If you look about it, it's because it's the integral of the luminosity multiplied by time over time. So it's the dimensions are energy multiplied by time. So we got a residual of about 10 to the 54 to 10 to the 55 ergs per second, ergs times second, where we expected to get about 10 to the 52 from the cooling envelope emission of a compact progenitor. So what are the options? It can be systematic error. Actually, this was what we thought. It can also be cooling envelope emission, interaction, or central engine. I will not go into the details. We can rule out envelope cooling, very high confidence. We can rule out interaction, slightly less, but also at high confidence. We can rule out almost all the systematics. So if there is a systematic effect which is driving this result, it means that we somehow don't know how to calculate the deposition of energy by gamma rays. So if we do something very wrong in the way that we model the gamma ray deposition, then this can drive this result. Now, if we assume that the result is really physical, then the only remaining option is a central engine, and we basically measured one of the properties of the central engine, which is the energy deposited multiplied by the time over which it is deposited. So the energy that we need here, these are the limits that we get. We need to deposit between 10 to the 48 to 10 to the 51 or 52, depending on how energetic is the supernovae, within something between 1,000 and 10 to the 6 million seconds, where the million seconds correspond to the lower energy and the 1,000 seconds to the higher energy. And with this, actually, we can estimate properties of the central engine. So if the central engine is a magnetar, then we measure the magnetic field. This is actually a measurement of the magnetic field of a magnetar, assuming, of course, that the energy deposition is by a dipole. It's a dipolar deposition, and it turned out to be 10 to the 15 Gauss. Roughly what you would expect from other considerations. If it's an accreting central object, whatever it is, it needs to accrete about 10 to the minus 5 solar masses over 1 week, or maybe slightly more over a shorter time. But one of the things which is interesting, I skipped it, you can see that you have different value for this, what we now think is engine activity for different types of supernovae. So the 1Cs has the strongest engines, and the 2Bs the weakest ones. So I would say, we still need a confirmation, that there seems to be an evidence for engine activity in all or almost all regular stripped envelope supernovae. This engine is not what driving the supernova itself. It's not what's driving the explosion. It might be driving the explosion at the beginning, but this is the explosion. It comes after the explosion and deposits this energy, which is later translated into the light that we see, and it contributes about 30% of the light around the peak in 1Cs and 10% in 2Bs. So this is the first result. Second question that I would like to go, so this is a different topic, is can a jet drive the supernovae and the GRB simultaneously? So now I go to the last type in my sequence. So these are GRB associated with this supernovae. So we know there is a jet, we know there is a supernovae. And we ask whether we can launch the jet and it makes everything we need. Explode the star, produce a nickel, give us a GRB, give us a supernovae. And there were claims that this is possible. And we wanted to test whether this is indeed the case, or do we need two different sources of energy at driving this explosion, one for the jet and a different one, or maybe associated one, but different properties for the supernova. So the way we did it is that we ran simulations of jet exploding stars. The first question, can a jet explode stars? The answer is certainly yes. So as the jet propagates, it deposits energy into the cocoon. This energy can be easily 10 to the 51 ergs. 10 to the 51 ergs is enough, and the star is exploded. But there is a big difference between central explosion and the jet deposited energy. And the difference is that in a central explosion, you deposit the energy at the center. In a jet, you deposit the energy all the way along the axis of the jet propagation. You see it here. And what happened is that the shock, instead of going from inside out, it's going from the pole to the equator in this way. Now, I don't have time to get into the details, but this type of energy release and propagation of the shock lead to this distribution of energy as a function of velocity. So I will 1 second on this figure. So on the x-axis, you have the logarithmic scale of beta gamma, which is the velocity, the relativistic velocity. And here you have the energy logarithmic scale of the distribution of energy per gamma beta. In a spherical explosion, there is a well-defined velocity, and most of the energy, or almost all the energy, is deposited in this velocity. And this is because of the central explosion. In the case of a jet deposited energy, you get a flat distribution in logarithmic scale. So putting it differently, there is the same amount of energy at the velocity here, and the same amount of energy at mildly relativistic velocities. Okay? And I will not show you, but we ran dozens of these simulations, different jets, different progenitors, different. All of them show exactly the same result because of this type of shock which is going from the pole to the equator. These are observations. These are not only GRBs supernovae, but some of them are. And we know you don't need this figure. In GRB associated with the supernovae are extremely energetic, 98 BW or 3DH. All of them are about 10 to the 52, almost 10 to the 53 ergs. And the jets themselves are around 10 to the 51 ergs. Not only that, forget about the jets. You should have a comparable energy moving at a Lorentz factor of about 2. The radio emissions that you will get from few times 10 to the 52 ergs moving at a velocity of gamma of 2 would be enormous. We can certainly rule it out. So we know in GRBs, in the supernovae, there is much more, about between 10 and 100 times more energy than we have in the mildly relativistic and relativistic component. And how can you do that? You need basically two things to your energy source. So one is something which is quasi-spherical and giving most of the energy, the 10 to the 52 ergs, and another jet which is go through. It deposits 10 to the 51 ergs, but doesn't, the exploding star don't care about it too much. But the jet is basically going out and doing whatever it needs to do. And then you get simply a superposition. So you see here, this is a spherical explosion. The dashed blue line is a jet explosion. And the black line is what you have when you do them simultaneously for the same source. So we release energy at the center, which we launch the jet at the center at the same time, and you simply get a superposition of the two. So my conclusion here is that the jets cannot supply what we need, and we need actually two types of energy release at the center: relativistic narrowly collimated outflow and Newtonian wide outflow. And the Newtonian wide outflow is about 10 to 100 times more energetic than the relativistic outflow. Now here it's interesting to look at the analogy between long and short GRBs. So in long GRBs, we are accreting about 1 solar mass. We expect something like that in the collapsar model. About 1% of that is what we see in the supernovae. and about 0.1% is what we see in the GRB. If we look at GW17 or 817, possibly also short GRBs in general, not necessarily. The accreted mass is 0.1 solar mass. We release 1% of that in wind from the disk and 0.1% in the jet. So this suggesting, not necessarily, but this analogy suggests that also what drives the supernova in collapsars is a wind from the disk. So again, it's analogy. Analogy can be misleading. Sometimes it can also be lead us to the right direction, but it's certainly suggestive. And from what I understood, there are now simulations that, for example, from my former student Or Gottlieb, suggesting that you actually get that from the disk. And the last comment on this topic is these are the distribution of velocity. Again, it's the same one as before. Velocity, or what is distribution of mass as function of velocity. These are all regular, or maybe not so regular, but stripped envelope supernovae without GRBs. So there is no direct evidence of relativistic motion from the jet, but you can see these are these estimates of these figures are done by Paolo Mazzali. Actually, for example, for 97 EF, this distribution was estimated 25 years ago. And it seems that there is some component which do not fit what we would expect from a central explosion, suggesting that it might be that the jet also is active in many stripped envelope supernovae. Not only an engine, but also a jet. And in order to know whether there is to identify the material moving at these velocities, what we need is good spectra at early times. This is the only time that that we are sensitive to these velocities, they're becoming optically thin very quickly. And here I hope that there will be a lot of progress. So my conclusion is that the vanilla type stripped envelope supernovae seems to be more interesting than just a spherical explosion. There are engines, possibly jets, and I hope we'll know about that more in the future. Now I'm going to a completely different issue, which is theory of shock breakout. I will not teach you or lecture or talk about the theory itself. I want to say just why is it interesting and why it is important and where we are now. So the shock breakout, so there is in any stellar explosion, there is a shock going inside the star. And at some point the shock gets close to the edge. At the point, this shock is radiation mediated. So all the energy in the shock is stored in radiation behind the shock. And it's relatively wide compared to other types of shock in astrophysics. And when it gets to the edge, to the point where the optical depth to the observer falls below some value, then all this energy which is stored in the shock is released to the observer. So this is relatively different than any other phase in supernova and cosmic explosion in general, because they are depending on radiative mediated shocks, which is something that you don't see in other phases of the supernova. This is true also for the breakout and also for the early emission coming after that, which is also the energy deposited by this radiation mediated shocks. And this is the first signal you are going to see, the electromagnetic signal. The first one you are going to see in any explosion. You cannot have an explosion with any signal that will not start with this shock breakout. And this shock breakout can teach us about the edge and about, for example, energy loss, mass losses just before the explosion. There is a lot of information in this shock breakout and the emissions that comes immediately after. And in order to understand it, and this information you cannot get in other ways. After the becoming optically thin, and you cannot have it anymore. You cannot get this information anymore. And it's hard to detect. It's not very bright. It's very early on. But here I think that we are going to have a revolution. Ultrasat is one example. Einstein probe might also play a major role. And all the surveys which are coming, we are going to detect many more shock breakout emissions for many different types of explosions, not only regular supernovae. And we don't have the theory that we need in order to interpret them. So in order to show you why we don't have the theory, I will give you an example. Oh, I will say something else before I get to an example. The point is that there are many different types of shock breakouts. They depend on the properties of the radiation-mediated shocks and depend on other things. So for example, the velocity plays a major role. It's very different to have a relativistic or Newtonian shock breakout. There's something called fast Newtonian. They have a different properties. It depending on what medium the shock is going into, where there's magnetic fields, where there are previously deposited photons, composition, density profile. I will not get into it, but each one of these scenarios is a completely different story. Each one of these scenarios need to be calculated, thought about. There are many complications. And so far, we understand only the most basic scenarios. So let's look, for example, at this scenario. And this is an important scenario. This is a shock breakout from a wind. Okay, so if we want to learn about the energy, about the mass losses, in cases that there is a significant mass loss, there is some wind which is optically thick. The shock goes out of the star, go into the wind. We don't see anything yet, propagating in the wind up to the point that the emission, the breakout, is coming outside of the wind. And we want to understand what we are going to see. We are getting a very complicated system. So we have there is a continuous emission from a region where the shock optical depth is lower than C over V. So the breakout already took place. There is a transition of the shock here from one type of shock, which is radiation mediated, to another type of shock, which is collisionless. The difference is that in collisionless, it's efficiently producing magnetic field, efficiently accelerating particles, but still everything has to go through this optically thick material. There is another reverse shock here. There is emission coming from the supernovae. There is an inverse Compton synchrotron and free everywhere in this region. There is a reprocessing of everything by what you have here. So it's doable, I hope, but it was not done yet. So far, now we do not know how to interpret emission from the shock, which from the early phases of supernovae, which are going through thick winds. Okay, and I think that this is an important thing that we want to learn, and therefore we need to understand this physics. I think that there will be progress because, as often happens, observation drives theory, and I think that it will happen here as well. Okay, let's go to another topic. Tidal disruption events. Okay, so I would like to say a few words. This is not a field that I work in. Actually not. I started looking at it a few months ago, so take everything that I say with care. But I would like to give the bird's eye view of the theory as I see it just from someone that's coming from the outside and reading the literature. So there are two pictures. So when we talk about the tidal disruption event, I will focus here on the flare in the UV. Okay, now I'm looking just at the main event in the optical UV, which is a flare that is around 10 to the 44 ergs per second, lasting about a month, maybe a few months. And we want to understand where this emission is coming from. So there are two prominent pictures. One of them is that the UV and optical flare is generated by accretion. So we have the star is disrupted, as we've seen yesterday, some material falls back, circulizes, producing an accretion disk. There is an accretion, and once we have an accretion disk, we understand what accretion disks are doing, or we don't understand, but we see that they release a lot of radiation, and this is what giving us the energy source for this UV optical emission. There is a less accepted picture, which promoted mostly by Krolik and Piran and Ryu, but maybe others, that the flare is actually coming from the shocks between the material which is falling back and starting doing circular or elliptical orbits with material that's falling back. So this continuous fallback of material from the disrupted star and collisions between them are what giving us the shocks. Okay, so these are two pictures, and now I will focus on the one which is mostly accepted. So how do we know that these are really TDEs? So we have several things which are consistent with the prediction. The first, it takes place in the center of galaxies. This is a good indication. The second, and this is actually the only one which I think is very strong, is that we don't see them galaxies where the estimate of the mass of the black hole is larger than 10 to the 8. And this is a clear prediction of the model from Martin Rees, and we see it. And the timescale is roughly what you would expect from this type of tidal disruption events. What doesn't work? So if we look at the luminosity, the accepted theory is missing 2 orders of magnitude. So if you look at the mass accretion rate and you look at what you would expect from an efficient accretion of this mass, and you've seen yesterday from Suvi, actually this mass, this accretion is highly super Eddington. The emission is sub Eddington. So we're missing 2 orders of magnitude in the luminosity. And if we look at the spectrum, we expect to see X-rays, we see UV. Okay, so also here we have several orders of magnitude in frequency, which is not what you would expect from an accretion disk. And another thing which is important and we don't know why and when there are jets. Now, it doesn't mean that there are no models that can, so the accretion disk model works if we set by hand the amount that is accreted, and we put, again I say by hand because we do not know how, we put material to reprocess the X-rays. So we can do it. This model is doing it, and it's doing it well. But we don't understand how we get the setting. It's not very natural. It's not what we expected to begin with. And also by now we don't know how this is happening. So, and there is another issue which I didn't see that was covered in the literature in enough details. And this is the fact that if you want to make a disk, you need to release energy. So no, you have gravitational energy, and you want to put a small disk which is accreted. You need to release somehow this energy. And you can estimate how much energy you need to release. And all this energy goes to radiation. It's mostly by radiation-mediated shocks, and therefore they are dominated by radiation. So you produce some radiation, and then you can ask yourself how you can hide it. And there are some ways to try and hide. I thought about everything that I could think. There are also something in the literature which I think they do not work. So I do not see how you can hide it. So basically, I cannot see how you can produce a disk and make the disk to give you the energy for the UV flare without producing first enough energy to produce the UV flare. Okay? So this is my conclusion, not necessarily correct. But as far as I understand, as far as I found in the literature, the disk is just there. So we assume there is circularization and continue from there. But I actually expect that there will be a very significant progress in this theory in the coming year. I think that this will be driven by simulations. The physics involved, at least at the first part of circularization and all this, is simpler in the sense that it is mostly hydrodynamics, maybe hydrodynamics coupled to radiation, and we just need better codes and more computational power. And the problem is in huge dynamical range. And there is a continuous progress, and I think that this is solvable. So if I would have to guess, 5 years from now, we'll have a much better, I don't know whether it will be one picture or another. I don't know where it will go, but it will go somewhere, and I think that there will also be a consensus about it. So actually, I'm quite optimistic about where the theory of TDE will go to. Maybe because I don't work with it. And the last thing I would like to talk about is the fact that we have more and more automatic tools. So these automatic tools are very convenient. They go to the web, they collect the data, they put it into the module, and they spit on the other side physical quantities. It's extremely useful, extremely easy to use. And I would like to give one example. So this is just one example. The example is example of MOSFET for TDEs. Okay, so MOSFET in TDEs right now is a standard. So I went to an observer that I appreciate very much, and I asked him, do you need to use MOSFET in your TDE paper? He said, certainly. Otherwise, the referee will not accept the paper. I'm not joking. This is what he said. It happens once. I said, okay, so do you know exactly how MOSFET works? He said, well, this is theory stuff. I said, okay, and what do you do with the data? I said, I don't know, I just report. So I actually looked at the theory that goes into MOSFET data to TDEs and try to understand it. I hope I'm doing justice. I would just like to say I have nothing against the model itself. So you will hear my concerns. But the model is good. Or the model is reasonable. Okay? So the model works like that. Forward modeling, we have parameters of the TDE, and we can calculate from that what is a mass fall rate. This mass fall rate has two components. One of them is the normalization, and the other is some time scale T0, and the mass fall rate goes like T to the minus 5. So this is not exact. This result is actually obtained by simulations, but all the simulation finds is T to the minus 5 cells because there is a very strong physical origin to this minus 5 cells. Then you have your m dot. You assume some efficiency, so the luminosity is proportional to this m dot. There is a free parameter called epsilon, and then you fit that. And you assume that there is a black body. Why? We don't know, but we see. So we assume that there is a black body. We fit for the photosphere radius, which is basically fitted for the temperature. So at the end of the day, there is one observational parameter with information here, which is a time scale. All the other is fitted by the model. So the luminosity is fitted by the model because of this epsilon. You can change epsilon, you change the normalization of the luminosity. You have no freedom about the temporal shape. M naught is not really important because epsilon is like fitting M naught. And the temperature, you just fit for the temperature. So the only available parameter is T naught. The machine gives you the mass of the black hole, the mass of the star, the impact parameter, and also the time of the merger, the time of the tidal disruption event. How can you do that? Well, what are the advantages of this model? So it's a reasonable fit to the data. Not always, but often. It's simple. And the assumptions are reasonable. There are different priors. For example, they assumed a group IMF. It's very reasonable. There are reasonable assumptions. What are the disadvantages? First, I guess you noticed, there are more parameters than observables. Okay? So we measure the priors. Basically, because you cannot fit four parameters or four physical parameters with one observable. So we measure the priors. For example, the group IMF goes in, and the assumptions about epsilon, there is some range of epsilon which they think is reasonable. All these are going into the result that we get at the end. And these assumptions are not justified. Maybe correct, maybe not. We have no observational evidence that these assumptions are the reasonable one. Well, group I would say yes, but for this epsilon, I don't know. And there is no predictive power. So it either fits the data or do not fit the data. Sometimes it does, sometimes it don't. But you cannot really say that these epsilons are reasonable or not, or you cannot do much. So, and by now, every TDE paper, you have all these values, which are driven by the priors of whoever wrote this model, which as I said is reasonable, but not necessarily correct. And I think that this is a problem. So I already said that, and I said most of it. So the problem is that most of the people use it as a black box. If we wouldn't have this black box, each one of us will have to take the parameters, actually and you get this model, okay? So you have the parameters, you have that theory, and you need to apply the theory. If you would have to do it yourself, you would understand what goes in, and then you can decide for yourself. You want to use it, you don't want to use it, how robust it is or not, okay? But no, it's a black box, it's easy to use, everybody uses it. It's a standard. So when I said, but why? There are better models. Why do you say, well, for standardization. So if I want to compare this paper to that paper gives a prediction of MOSFET. This paper must give a prediction of MOSFET, and you can compare them. Okay. Another issue. The statistical errors are irrelevant. So the main errors here are the errors about the assumptions of the model. Okay? So for example, we assume epsilon is constant. It's not necessarily constant. What error this introduces? Much bigger errors than the statistical error for this specific model. But all these errors are reported and treated as if these are the errors that you should work with. I think this is a big issue. And what about the real systematic errors? These are hard to find, practically impossible, nobody even bothered. So my view, this is my view, the advantage of automatic fitting is easy to use. The disadvantage, it's too easy to use. And I think that most will agree that we need to know the limitations of the models that we apply, even if not understanding everything. Not everyone can understand everything, but we need to understand the limitations, the big story, what is going on. And we need to remember that the statistical errors which all these mechanisms spits out, usually, they just tell you if these are very large, then okay. But if they are very small, they tell you nothing about the real error of the model. And so this is my conclusion. It's a bit assorted. So these are some prospects, future prospects, in my view.
Thank you very much. Oh, okay. Many questions.
So can you please briefly explain how did you exclude CSM interaction as an energy source for normal type of disease?
Yes. So energy interaction has several observables which you don't see here. For example, we do measure X-ray and radio, so we know how much mass there is in which the fastest ejecta is moving in, and this is very far from what you need. We don't see any narrow lines. And another thing which is important is that if you have interaction happening in front of the ejecta, then there is no reason for the peak of the interaction and the peak of the nickel to be at the same time, because the peak of the nickel is the time where all the ejecta is becoming transparent, and the peak of the interaction is when the interaction takes place. And we see that there is one peak in all of them. So in one of them you can have coincidence, in two of them you can have coincidence. So what you need is to have interaction inside. It's not necessarily impossible. For example, think about a disk. You engulf the disk very, very fast before you see anything. And then you continue to have interaction with this disk inside. Now, this is the only option that I can think about. It's highly contrived. It will give some signs if the observations are early enough. And it will be, then the observation will be strongly depending probably on the viewing angle. We don't have any significant evidence for viewing angle playing a major role in this supernova. So this is why I say I cannot completely rule it out, but I think that you need a very contrived scenario scenario in order to do it this way. And also why it should be always this similar to the amount so always 20-30% of nickel. Why not much more?
Yeah. Mickael.
I've got a question and a comment. I'm going to save the comment for it. As a developer of a very large open source fitting tool, I actually completely agree with you. So I think using it as a black box is incredibly dangerous, and I seriously suggest people don't. I wanted to get your opinion on the other flavor of TDE models that you didn't really talk about, is the idea that, which is backed up by numerical simulations of Steinberg and Stone, etc., that you have circularization. That emission, I agree, is a bit of a problem where that energy is going, but then it forms an envelope, and then the envelope is cooling first, and then later on it can produce an accretion disk.
Maybe this is the case, but for example, in this specific simulation, the actual light curve that they measure, which fits rather well what you see in the UV flare, is coming from the shocks leading to the circulation. So in this specific simulation, you get exactly this result. That the energy which is released on the way to circulation, and they do not really see full circulation over there, but it's not really important. But the shock that they have is giving them what they need in order to produce a UV flare. And this is what they measure. So I think that...
I'm talking specifically more about so not this flare itself, but the cooling afterwards, the plateau emission afterwards.
Yeah, actually this is I think that there should be an accretion disk. there is an accretion disk sometime, somewhere. I think that this accretion disk is what's responsible for the long-lasting emission. So probably there is an accretion, maybe even you accrete most of the mass, but you will do it over years. You have actually limits on how much you can accrete at early time, which is very low, about 10 to the minus 2 or 10 to the minus 3 of the mass that you have there. I think that there is an accretion disk working there. We don't know for how long, certainly 10 years, this is what we observe. But if I would have to guess, you have enough for about 100 or 1,000 years of accretion. My guess. Well, educated.
Pumps?
Thanks for the nice talk. You said about the TT part. You said that from the circularization, there is energy released and that we cannot hide that. Do you have an estimate on what could be the luminosity of this and in what range we should expect it to?
Well, in what range, I'm not sure. You can do many things, but it should be the Eddington luminosity. So the problem is the following. It's even stronger than what I said. Whenever you need more than the Eddington luminosity in order to circularize, and you actually need, if you have shocks at a radius, so let's say that the pericenter is 10 to 13 and the epicenter is 10 to the 15. For typical parameters, shocks below 10 to the 14 will give you more than Eddington luminosity. And then what you would expect to see is actually a plateau. It's Eddington luminosity, because every energy that you release above the Eddington luminosity and you release everything in photons will drive wind. And at the end, the radiation that will come out of this wind will be comparable, slightly larger, slightly smaller. You can play with it. But you expect to have plateaus at the Eddington, and we don't see them. So if I would have to guess, then not only that the flare is coming from shocks, it's coming from shocks taking place high above the pericenter. But, yeah, my estimate.
Yes, Peter.
Yes, I think your first work here with Rodriguez on the stripped envelope supernova, saying that they need some sort of extra engine, is very important, but I don't think it's right. Because there are many of these supernovae that have been modeled in great detail, and they fit with nickel only. So you don't need anything else. With hydrodynamics and non-LTE, Anders have done 11DH, ACAT is done. I think your problem is that you are estimating the nickel mass from the tail, and that's not so easy as you think.
I would just say that Solerman will be, and Afrogiati will not agree with me.
I say we need more nickel than the modelers think, but I'm not saying that you can't do it without nickel.
Oh, okay. Well, there are many more questions. Smaranika? Yeah.
Thanks for the nice talk. So I'm going back to the GRB portion. So where you showed like the energy that is like from spherical energy and the basically jets energy as well can basically take part in explosion. So I have question about more about the physical scenario about this. So is this a jittering jet? What are you actually considering here? Like you have the spherical energy?
No, I don't have any jittering jets. And
what are you
and I'm doing something which is very simple. So we put both the jet and the explosion by hand. So in this specific case, it was a spherical explosion, so just release of energy at the center, and a jet which is launched from the inner boundary. Okay? I can tell you, well, I didn't do it, but if instead of having a spherical explosion, I would have a wide angle, say 60 degrees, it will be the same. Okay? So if you look at explosions of anything which is larger than about 30 degrees, then this explosion cannot propagate like a jet. A jet, you need a collimation, and you have this, and you need some maximal angle for that. Actually, I don't know what is it, and I don't know about anyone that did it. So if anyone, there is a project. So anyway, there is a maximal angle over which you will get a jet which goes in, above which you will get something which is quasi-spherical. Yeah. Okay, but, so I don't know where this spherical is coming from, but wide angle wind from a wind is...
Yeah, that's very interesting that where the physical mechanism actually coming from. Yeah, thanks.
Yeah, I will just one thing about what I said to you I want to add. It might very well be that we are missing something about the nickel. So not only us, everyone which is making this modeling this is a viable option that we need to explore and to really rule out before we go to completely to the engine. I agree with that. Okay, I agree.
Okay, Selma.
Let me entertain your rights. And there is an engine. Why is there then an engine in these exploding helium stars? And is there then, if that is the case, why would there not be an engine as well in a helium core that's exploding in a hydrogen envelope? What's the difference between the two, or are we not seeing it there?
Okay, so first of all, there can be engines in the hydrogen-rich supernovae, and we'll never be able to know it. So the same engine, the same amount of energy deposited in type 2Ps, no chance that you will see it. Okay? So I don't say there is, I don't say there isn't. One thing about one option that we have for these engines here is simply magnetars. So we know that about 10%, few tens of percent of all supernova produce magnetars. Just count magnetars in the galaxy, you know the supernova rate, you know the lifetime. So there are estimates up to 75%. So many supernovae, regular ones, have magnetars. This magnetars is exactly what you need to power.
It's not something special of the helium stars.
No, it should be rotation.
It's just. Oh.
This is my guess.
I'm with you, but that's a different. Yeah.
Okay, many great questions. I think we'll have to take the rest of them over lunch, but let's thank them. And our next speaker is Smaranika Banerjee, telling us about modeling kilonovae.
Yeah. So hello everyone. I am Smaranika Banerjee, postdoc here at Stockholm University, working with Anders. So I'm going to talk to you about modeling kilonova, and I don't have to give any introduction to this crowd, but yeah, so you already know that the kilonova is basically the transients powered by the radioactive decay of freshly synthesized heavy elements. The origin of heavy elements is probably this compact object merger, so we are excited about them. And I will share the enthusiasm of the previous speakers that we are in this great era of this era of large service that is coming up. So I have just here written a very few subset of it. You have seen already a bigger set of it from Mansi and the previous speakers. So we know that we have Ultrasat and UVEX coming up in the UV. We have Rubin coming up in maybe end of next year or early 2026. We already have ZTF, and we have JWST online. Mansi talked about many other infrared telescopes like Winter and others. So this is very exciting era to be in working in transients, and also especially in kilonova, because you have already seen this many times that the first spectra up to a few days. Here up to a few days of the first and only confirmed kilonova so far, you know that it will be bright in starting from UV, moving towards infrared. And also we heard from Nial and others that so as the JWST is online now, we can hope to have the at least similar to, this is not confirmed kilonova, but candidate kilonova at least, even without GW association, this kind of spectra which can be potential kilonova, like you have seen this, that this is the counterpart of GRB 20307A, and this is possible, we possibly see a emission line of tellurium, or we also kind of thought of signature for tungsten or selenium. Yeah. So this is a very exciting era. Right now, the number of kilonovas looks glim, but I share the enthusiasm of Mansi that I think that we are going to observe in the next era. So what to do when we detect the next one? So well, of course, the firstly, we probably go for semi-analytic modeling or something, but then we want to understand them in more detail. So we want to be prepared theoretically as well. So that is where we modelers come in, I guess. And so if you ask any of the modelers that what do you need, so I tried to give a very simplistic picture of what we can start with. Of course, you need a proper radiative transfer code, hydrodynamic simulation, those are later, but just what you need once you have that kind of a radiative transfer code. And so, we need some kind of ejecta structure. So life is not, after the neutron star mass, life is not as simple as this spherical cartoon I have shown here, but pretty more complicated. But so many of our numerical relativity friends and hydrodynamic colleagues are working on how this ejecta exactly should look like. And also, depending on the binary properties, this ejector structure and which element is actually synthesized will be different. So, yeah, we need what materials is exactly ejected in the structure and what elements are there to understand anything from our simulation. And the second thing that you need is probably more of a bottleneck for kilonova or calculations is the microphysical input. So in radiative transfer simulations, we actually try to calculate how the photons are moving through these heavy elements, heavy ejecta. And you actually want to know the cross sections of the photon matter interaction. So we need these atomic inputs, atomic data for heavy elements, like all the elements can be synthesized. When you are in photospheric phase, in the first few days after the kilonova, your life is relatively simple. You probably just need, because you are in at least locally thermodynamic equilibrium position, and your ejecta is mostly optically thick, and so you can go away with relatively lesser amount of microphysical input, like only probably opacity. If you know this, you can say something. I will not say, I won't have much time to discuss about this. I just want to give you a summary of decade-long effort, almost a decade-long effort of going on in this area. So many people have tried to calculate the opacity for heavy elements to give you good predictions of light curve starting from Kazan et al. 2013. The first infrared spectra and light curve for kilonova has come, and now you have this kind of opacity tables readily available for different compositions. So here is just an example of the opacities of several composition of the ejecta suitable to calculate the UV light curves, and there are also for optical light curves in other papers that is available. There are now 2 databases for opacity, so if you want, you can just go there, check if your assumptions are correct, and or use those as it is. So now when we are relatively okay with microphysical input, now at least the first set of calculations are there, now we probably want to think of more about these ejecta structures. Obviously, there are many calculations going on for many years, but you want to put everything together, right? A more realistic ejecta structure, microphysical input, everything together. So the first set of kilonova calculations have been done taking these detailed microphysical inputs and very simple ejecta structure. For example, this is a power law type of ejecta. As you can see from here, this is the density, and then you use your detailed microphysical input, and for the polar viewing angle, if your viewing angle is around here, this is a 2D simulation, you basically see bolometric light curves, something like this, and this is the UVW and Swift filter, and this is the G-band, so something like this. So now you want to move towards more realistic ejecta structure, as Udi has given a lot of introduction of the jets. So so you know that our ejector is not so simple. If a jet probably get launched and has moved through it, and so this jet will be modifying the ejector structure, right? So what if a relatively narrow jet like 6.8 degree opening angle move through the ejector and have something like this? Then actually from this simple, you see that from this simple ejector structure, as you move towards this jet interactor ejector, you see the light curves actually get something like this, a bit fainter. This is bolometric light curve, but still, if you try to see in the like the UV light curve band or the Z band, you don't see much much difference in there. So, but the jet angle, we don't know exactly like they will be narrow or what exactly will be their opening angle. So if we go for a bit wider jet that will modify the ejector more, then you see something like this. So I want to point out this UV band. So you see the light curve actually get dimmer. So this is dimmer because this jet has actually modified the ejector to have a relatively thin layer. So we have previously seen in the ejector, if we put a relatively thin layer in the outside, then we actually see the light curves getting fainter. So and all of this have just the lanthanide free ejector because we are observing in polar direction. More realistic abundances can be put in here. So so to say anything about the jet structure, if I may dare to say, from the light curves can be probably possible. Of course, the models need to be more modified, but if we observe from ultrasat, we can at least say difference between the white jet interactor ejector and the power law type ejector easily. From the ZTF is probably still in G band will not be so possible, but with maybe ultrasat can help us in here. So this was the photospheric phase where many models and the modifications have been done. So now we have JWST, so we want to know the nebular phase spectra as well. So when you move from this photospheric phase of this optically thick ejector to optically thin ejector, when in nebular phase the ejector has expanded enough, then your life becomes much more complicated because you don't have this equilibrium anymore. You need many more processes, cross-section of many more processes. And just to give you an idea, we have this we are far away from reaching where we are at a photospheric phase right now. So you can see the many more cross sections are just taken simple assumption or the constant right now. So we want to ideally calculate all the cross section for all the elements, but this is a very big dream. So we start with a very simple one, this recombination coefficient calculation, which has direct effect on ionization and spectra. So I don't have detailed time to actually talk about everything. So I just want to show you one thing. So we calculated this microphysical cross section for a few light R process elements, like not as heavy as lanthanides, like lighter elements. So here I'm showing you selenium cross rate coefficient for recombination, which is one of the elements that is predicted, as I showed in the very beginning of the picture. So if we used to use a constant rate, now our calculated rates show you there is, of course, it's not constant, and we just want to see the effect on the spectra. So this was the calculation of spectra, the total spectra of with using all the light R process elements, and this is the individual contribution of selenium, different ionizations. But when you use these detailed rates, you can see the spectra becomes different. So this is just preliminary, but it still shows us the importance of actually calculating microphysics and to actually understand what elements are there or get any sense out of the good data we are going to have in era of large surveys. So this is my summary that, we are at very good progress in photospheric phase, and nebular phase is pretty new, and we are going there. So thanks for your attention.
Thank you very much, Smaranika. Questions? Yes, Mansi.
Nice work. Go back to your selenium slide.
Yes.
So because there are all these transitions that have not yet been calculated, right? When we go get JWST spectra of candidate kilonovae, what lines, should we be looking for? Because there appear to be some selenium transitions as well in the right range. So, how do you know if it's tellurium versus selenium versus something else?
Yeah, that's what we want to. So that's why this. So I think in mid-infrared you see. Okay, there are a lot of slides to go back. Okay. But so in mid-infrared, I think these two are actually not yet settled. So we still don't know if this is tungsten or selenium. I would be very happy if I can tell you right now, standing here, that yes, this is selenium or so. So since our models had only lighter process elements, so that's why I actually checked for selenium. If it was like higher, larger the lanthanide rich ejecta, then there is possibility to produce tellurium and tungsten as well, and I want to check there. So definitely that is the next step. I still did not completely.
Right, because in the optical it's easier, right? You can go for 2 lines or something, and then you know, okay, if you see this silicon line here, you should see this other line here, right? So you have an anchor here. There is 1, maybe 2 lines to work with. It's a little bit trickier, and there are many more possibilities.
So that's why microphysics become really important here, as you just showed in my spectra, that when I am actually including one detailed cross section, and this spectra is changing much more, and there are so many more cross sections yet left. And also in radiative transfer side, there is many more assumptions. We are definitely going in the right direction, but we need to see some more, I guess.
Thank you.
Yeah, thanks for this.
Neil?
So there's also interest in the possibility that collapsars could produce our process. Do you think that you will be able to transfer your modeling over to look at that question in the nebular phase?
Yeah, I think this is definitely possible. There is no basically we had some discussion about this. So there is no potential barrier in the sense just you have to change the ejecta model in the sense, right? Because you want to go to collapse a lot more ejector mass and so on. But if you're talking about the microphysics, we already have the input. So it's pretty well possible and very good next step, I would say. Thanks a lot for question.
Okay, I do not see any more questions, so let's thank Smaranika. And our final speaker of this session will be Jan van Roestel, who will tell us about a different survey, BlackGem.
Yep, sounds good. All right. Well, thank you for this opportunity to give this talk. I have to say I'm very, very happy to be able to give this talk because even before I was an undergraduate, I was already hearing about BlackGem, and I'm very happy to say it's finally there. So I'm Jan van Roestel. I'm a postdoc fellow at the University of Amsterdam, and I'm also a part-time project scientist for BlackGem, or at least in theory, part-time. The PI of the project is Paul Groot. Steven Bloemen is also working on it full-time as a manager of the project, and Paul Vreeswijk is working on the software to handle both the telescopes and the data. But there's also many more contributions from the wider BlackGem team. Oh, and by the way, it's a project by the Radboud University in Nijmegen, KU Leuven, the organization of Dutch universities, and 12 minor partners, I guess. Right, so not going. Go back, no. I'm going to the next slide. Ah, there we go. Right, so to understand, to start with the history of the BlackGem project, it's been planned a long time ago, and actually before the 3 BlackGem telescopes were built, a prototype telescope was first constructed. Scientifically, it's a very different telescope, but the design of the telescope is identical. Just to test the technology, the Marek telescope was put on Sutherland, and the science for this telescope is to get simultaneous optical and radio data by basically looking wherever the Meerkat array is looking. And this one's been operational since 2017, and that's actually been quite nice to both test the hardware and the software. So what is the BlackGem hardware? So it's a 65 centimeter telescope with so the main mirror is over there. Right, then we've got the secondary mirror over here, which actually you can be able to move it, so you can move it, use it to focus, but also to correct any tracking issues. So that's been very useful. And then finally, there's 3 lenses here, which are also the last one you can move around, so it actually can function as an ADC. It's also quite a neat trick. And then at the end of the optical path is a CCD, which is shown here. It's a 10K by 10K CCD, so we cover quite a large area with a single chip. So what this setup gives you is 0.56 arcsecond pixels, 2.7 square degree per telescope, and we got also a filter wheel, which is somewhere here, with 6 filters in there. So with this telescope, we typically use 60-second exposures, and in the widest band, we can get down to 21st and a half magnitude. So just to show you what the filters are, these are the standard UGRI-Z filters, plus in addition to that, a wider band Q filter, and the reason it's called Q is that the only letter that was left. But you can think of it as roughly G and R and moved slightly redward. So this is the Q filter in orange here, right? So just to show you a picture you can make with this telescope. So this is the Orion Nebula, thinking all filters combined together. So I think it nicely shows the capabilities of the instrument. So basically we built a prototype, and in 2019 we put 3 additional telescopes were built, and they were put on Lucia. And if you've been to Lucia, you've probably seen the 3 towers already. They've been there for quite some time. We had a bit of bad luck at the start of 2020. We had some mechanical issues, and for obvious reasons, we were not able to travel to Chile for at least 2 years to be able to fix them. So it took a while, but we're finally there. BlackGem is now operational. And it's still with an asterisk there, so this is just the number of images we've been getting over the last few years. So you see that one of the telescopes has been operational for a year. The other one had some, there were some logistical problems which caused a huge delay, but that one is also working out. The middle one, BlackGem 3, which is here, this one, that was operating, but the CCD needed to be sent back to the manufacturer, but that has been fixed now. So we hope to have the final one back in operation in the next few weeks. So with that, finally the whole operational will be the whole array will be operational. So just to briefly show you what we do with all the data. So the telescopes are fully robotic. We don't have to be there. We operate it remotely from the Netherlands. It's closes automatically with weather, which is what I understood very important, since actually Lucia has a very bad storm at the moment. The data is automatically uploaded to the Google Cloud, and there it's processed. We do automatic image differencing. So just an example here on the right, where we have a new image, reference image, and a difference image with the transient on there. And that's automatically processed, and the transients stored in a database. So that is the advantage of having a prototype. This software has been basically in development and has been tested since 2017. So what is the main science driver of BlackGem? So it is designed to follow up gravitational wave triggers by LIGO and Virgo. So as we've heard already, LIGO and Virgo are searching for gravitational wave signals, and specifically signals that are expected to contain a neutron star component. We're going to follow up, and of course the LVK detectors will give us a rough sky position. BlackGem will follow them up, and we will then send on the counterparts, or the potential counterparts, to larger telescopes for identification. We were hoping to be online at the start of 04. That didn't quite work out, but we're definitely operational in 04B. So we're now here, and that is what the main goal will be for the next year. We actually also followed up 240422 on this in April. So we got the alert from LIGO Virgo. BlackGem was automatically triggered, so there's no human in the loop there to actually approve it. It actually does this without human intervention, and it started to follow up the region where the potential kilonova would be. So in this case, we had to look at 99 fields. It wasn't quite flawless. We accidentally reversed the order of fields, so we started on the outside, moving in. We definitely fixed that little bug in the pipeline. As all the other telescopes, we did not find a counterpart. Right, so when there's no kilonova triggers, we actually do other things, and there's people in the team interested in all kinds of optical time domain astronomy. There's a very small part interested in solar system stuff. There's actually quite a big part, quite a big part of the collaboration interested in Milky Way objects, so variable stars. And of course, we also do transient science. So BlackGem has been, for the last year, been mostly collecting new reference images, because the LaCie site is much better than Sutherland. But we already have been using old reference images from the prototype telescope to already check if we found transients in there. And actually, we have been reporting quite a few transients to TNS already. I think we're about 300 now. And about half of them were actually first detected by BlackGem. So that at least shows us that there's still a lot of discoveries to be made, especially in the southern hemisphere. So I already mentioned BlackGem is doing other things. So the main survey will be the gravitational wave trigger mode. We will, if not searching for kilonova, we'll do a local transient survey, so focusing on nearby galaxies to find transient, low luminosity transients, and find transients early to do early phase transient science. In addition to that, we also have a fast synoptic survey, which is what you call in LSST speak the deep drilling surveys, mostly focused on galactic science. And we will also build a color map of the entire southern sky. So what is the local transient survey? That's where the bulk of the transients that we will start reporting will be from. So we'll focus on 226 fields. Those are the red ones here. And those fields have been selected because they contain some of the closest galaxies. So as I mentioned, the goal here is really to find low luminosity extragalactic transients, and also try to find them early. So what we'll do, we'll observe these fields 3 times per night, and each visit we will get a U, Q, and I image. So that means we won't find many transients, but the transients we do find will have very high quality data on them, and very high sampled light curves. In addition to that, we also once a week roughly look at a wider selection of fields, that just to basically keep track of what's going on in the southern hemisphere, and that if a kilonova trigger happens, we have at least some idea of what happened in the past on those fields. So just to show you a few examples, on the left you probably recognize what this is. We're at a supernova 1A with this very nice bump in the I band over there. So that's shown in the red. The yellow points are the Q band filter, so that's the wideband optical filter. But in purple you see the very nice U band data. And here on the right you see an example of a nova in the LMC. The LMC and SMC are also fields which are in the local transient survey, which we're monitoring frequently or multiple times a night. So I use this opportunity to sneak in a little bit of galactic science, which is actually my main interest. So as I mentioned already, we will do deep drilling observations, and those are really focused on exploring the very short timescale variability of hours down to minutes. And you of course find flares, outbursts, rapid rotators, high frequency pulsators. But what I think are the most interesting sources are the compact object binaries, and I think I can convince you that these are the most interesting too. But before we go into that, the way we do this is basically by looking at one field continuously for half a night. And we cycle through the filters, so we get U, Q, I, Q, and then repeat that sequence for a few hours. So we get a light curve like this with 3 colors. And we can use that to find short period variability. So we do we especially do period searches for that. And this is an example, a known object that that shows eclipses every 39 minutes, I believe. So this is what I care the most about, and I'll convince you that these are interesting. First of all, these short period white dwarf binaries, they are the transient progenitors that we talked about today and especially yesterday. And they're also gravitational wave sources. So this is a different aspect of gravitational wave astronomy and large-scale surveys. We actually want to find these sources that orbit each other in periods of less than an hour, and actually will be detected by the LISA satellite when it launches. And most numerous sources that LISA will find will actually be the double white dwarfs and the accreting double white dwarf systems shown here. So I'm also going to sneak in one non-BlackGem slide here. This is on my own work, which I've done with ZTF. So actually, we also are keeping an eye out on galactic transients. So we had a very nice picture on the website to show all the galactic transients. These are all the outbursting stars that you find if you search through the ZTF data. And these systems are all white dwarfs which are accreting from a companion star. I mean, not all of these will have very short periods, but about a few to up to 10% are expected to be these very short period white dwarf systems, which are gravitational wave sources. So what I actually had a student do is basically take this whole catalog and see if we can actually recover some of these short period signals in the data. And I was actually pleasantly surprised that we were able to find, not one of them, but actually 4 of these using this method. In addition to that, you're also finding lots of things that you did not expect. You see some very long timescale outbursts of these white dwarfs. Actually, this outburst lasted almost a year. And I think a few of you have been confused by these sources, thinking that these are superluminous supernova, which after you get a lot of spectra, you really see that these are at 0 redshift. So if you happen to find more of these, please send them my way. So with that, I'll end here. So this is an overview of all the BlackGem partners, and actually the overview paper for BlackGem was recently put on archive, so you can read more about it there. Thank you.
Thank you. Questions for Jan? Yes, Kishali.
So this is more of a technical question, but how are you doing the Q-band photometric calibration?
That's a good question. So we calibrate all bands based on the Gaia XP spectra. So we use the spectra as measured by Gaia. We calculate the magnitude we expect to find in our filter and all 6 filters, and use that to calibrate it. It's especially useful in the U band as well. Yeah, it's actually some very neat work done by Paul Vreeswijk. Yeah.
Mansi first.
Congratulations on getting all of this working, hard work here. I wanted to ask about your TNS slide where you said you have 300 discovered transients. What is the breakup of those, if there are spectra? Are they mostly supernovae, dwarf novae, CVs?
So these are all extragalactic. I think I've looked into, so not all of them have a classification, but I think the ones that did were about 50, like majority 1As and a few type 2s and I think a few unclassified ones. Like
should be all the novae in LMC, SMC as well, right?
I think it was the nova I showed was the only one we found so far, but I haven't checked recently. But in principle, yes, we should be able to find all of those if they go off.
Jakob?
It was a technical question, but first, very nice to see it operating. How similar are the systems in the end? Can you use the same set of references between the different telescopes? And then a second question, will you continue building more, or is that the setup now for the...
Let me answer the first one first. So the telescopes are identical. Of course, Sutherland and LaCia are definitely not identical. The conditions are much better on LaCia. So the images we took on Sutherland have a typically much larger seeing value. So that's why we've been basically rebuilding the reference images. But we are using them, but we just noticed that we're limited by the reference images we have. So the second question is, yes, the plan is to build 16 of them. Of course, there's funding needed for that, and I don't know if you followed the politics in the Netherlands. We don't have a very science-friendly government coming in now, so it's going to be a challenge. But, I mean, it's a very modular approach, so if there is more money, we'll definitely want to build more.
I think Jesper first.
So there are a few other survey telescopes in the south. Are you sort of planning to coordinate your efforts, or are you doing something completely different?
I think the consensus within the team is to try to find our own niche. So especially with LSST coming up in the future, that's why we decided really to go for the shorter time scales and the higher sampling of both galactic and nearby galaxy fields.
It's very nice. So I was surprised to see that you're using Google Cloud to do your data transfer, data processing. Can you tell us more about that?
I think this was before I became project scientist. I think there was some negotiation, and BlackGem is considered an educational institute, which is why we got a better rate than just regular companies. But I don't know the exact details of that deal.
But you're storing all the raw data.
Yeah, all the raw data is stored on the cloud. Yes, it does help us scale up and down. Well, basically with no effort. And I think Google agreed to host all the data once the project finishes, the archive.
So Christopher was first.
A question on your high cadence mode. You were changing filters a lot. How do you manage this exactly?
So there is a filter wheel in all telescopes. So there's a 10-second readout time, and within those 10 seconds we can rotate the filter. So yeah, that doesn't give any penalty.
So has the local transient survey already started?
No, so we did do some test observations. That's what the light curves I showed were from. But we've been trying to really get the reference images built. We're satisfied what we got now. So we are now transitioning to doing the local transient survey and doing the reference building in the spare time. So yes.
What would be the expected depth in each of the three filters?
So in Q band we reached 21.5 in dark time. For the I band it's 1 magnitude shallower, and U band it's another magnitude shallower. U band is still challenging.
So you roboticize these telescopes, and you have 3 of them. Have you run into any specific problems roboticizing 3? I assume they observe simultaneously, right?
Yes, they observe simultaneously, but they are doing things independently.
Right. So So if one of them goes down, that doesn't affect the other two?
No.
Okay, great.
Okay. Yes. Thanks for the talk. The prototype that you mentioned running parallelly with Meerkat, right? So have you found any nice, interesting transients there within optical and radio?
I am not very much involved in that part of the project, so that is really Meerlicht versus BlackGem. I'm really part of BlackGem. As far as I know, we have been unlucky. There were a few FRBs found, one or two, I think, with Meerkat, but at that time, Meerlicht was not looking at the same field for some reason. So I think the answer is still no. Not sure though.
Okay, any final questions? If not, let's thank both speakers again. And I believe we break for lunch.
About the ZTF sample and how that is going to help and change cosmology. I'm not convinced yet. I'll give you a 10-minute warning.
Okay, thank you very much. Jesper, thank you very much, Adam. It's an honor to present to you guys the ZTF survey, and it's an honor to talk after Adam on cosmology. So, we've been talking a lot about ZTF today already, and yesterday too, and I'm going to give you the point of view of people who haven't published so much, not 1,000 paper in the last years, but we are going to release a very significant sample as we speak. Okay, so ZTF is this very large field of view camera that is observing the equivalent of a blister that you hold like that in the sky, equivalent to HSC, which is, I believe, something like a grain of salt that you hold like that in the sky. So it has a massive field of view. We are able to observe in 3 filters up to a depth of about 20.5 magnitudes. And we are covering almost 4,000 square degrees per hour. This means that we are able to see the full visible sky more than once every night. And because we do that, we have an amazing cadence, and we are observing a lot of times the same place in the sky. And so, unlike all the survey before us at the low redshift end for cosmology, we used to be limited by our ability to find nearby supernovae because the universe was too small. And so in comparison to higher redshift sample, where we had to point with a big telescope in one part of the sky, the pencil beam behind that, the number of supernovae you can find was pretty high. And so for a long, long time, it was actually the low redshift survey that was difficult to acquire. And ZTF is changing that. And so you see here the GR and I band observation for the first 2.5 of observation from ZTF. So this is from the beginning of the survey, mid-18, to the end of 2020 when we moved to ZTF phase 2. And you see here in G, R, and I that we typically have a cadence of about, trying to learn how this works, about one to a few days, same thing in R band, and slightly longer in the I band of about 4 days. So this means with this camera, we are able to have amazing cadence in our light curve. So this is showing you a plot from the Pantheon Plus study that was published by Dan Skolnick of the worst supernovae that enter the Hubble diagram, the average supernovae from Penn-Star enters the Hubble diagram, and the best supernovae you can get in the Hubble diagram. If you compare that to what we have having in ZTF, this is the same plot showing you it's really annoying to point this way. The worst supernovae we are allowing to enter the dataset, the average supernovae, really, this is a randomly picked average supernovae, and the maybe slightly overshoot type 1a supernovae we have here for the high cadence field. So we may not need this cadence to do cosmology, but it's very good to know that the worst thing we are considering is this kind of object. And so to give a sense, we require to have 2 points pre-max, 2 points after max, at least 2 bands, and at least 7 points in the phase range from -10 to +40 that is shown in gray here. This is where the light curve fitter are well sampled and well trained. So this is because we have pre-max, post-max, and the dense sampling, we are confident that we are measuring well the light curve parameters. And so by doing that, for the last 2.5 years, we have acquired nearly 3,000 type 1a supernovae with cosmological quality. I will detail the number after. But this is how it looks in the sky. So not only we have supernovae, many supernovae, but we have them everywhere in the northern sky. So this square you see here is a footprint of LSST, of ZTF I'm sorry about that. This is a footprint of ZTF in the sky, and the gray band here is the Milky Way, obviously. And we see that we are randomly sampling everywhere in the sky. Not only the number of supernovae, but also the properties of the supernovae we are acquiring. The redshifts, the number of supernovae you see here, the redshift you see here, this is the average redshift size, the stretch, the lack of stretch. Trying to learn how to do this work, lack of stretch or lack of color here. And you see that we seem to have no bias there. There are some places where you have more scatter along the Milky Way, for instance, because we have less supernovae. And here you see that the average redshift is the same, or the average stretch seems to be roughly equally distributed. And this will get better and better as we're acquiring new data. And with this release that we have, this is what is arriving, that you may have seen arriving on the archive, and it's not over yet. We're going to have few more ZTF papers in the next few months. And this is only using 2.5 years of observation from ZTF. So this is about 45% of the data we have acquired. With this 45%, we have acquired that entering cosmological Hubble diagram 2646 type 1a supernovae. In comparison to the latest state-of-the-art DES paper here, this is the number of supernovae, nearly a bit more than 1,800. This is all redshift combined. This is what have entered the DES 5 years analysis that's been published a few months ago. In comparison, for the same redshift range, they only limited to modern survey because the rest of the other older survey was not as well calibrated or not as well controlled in their selection function. So for modern supernovae, they have about 200 of those very nearby supernovae. We have 10 times the size in only 2.5 years. We have about 20% more type 1a supernovae that have been acquired for cosmology in the last 20 years. So ZTF, in that sense, is extremely impressive. And what is very impressive, too, is that on all the type 1a supernovae we have detected and classified, nearly 3/4 of them at the end up in a Hubble diagram. So this is very, very strong for this kind of survey, because we have a very dense sampling. What is very remarkable with ZTF for cosmology, for the control of the selection effect, for the quality of the light curve, is that we don't need to trigger for the light curve. We only need to get a spectrum and trigger for the spectra, but we don't need to trigger for getting the light curve. So the detection and the follow-up is the same instrument, which means that we get a full light curve. We have the upper limit, we have the rising part, and we see it for a long, long time, as long as it's visible. And with this first major release that we are doing with ZTF that we call the DR2, we are publishing 21 papers in this special issue from ANA that is about to arrive. And so you may have seen already a few of those papers online. So there are 7 papers on archives. There is 1 paper already accepted for M1A physics. And today I will focus on the part that is connected to the sterilization of the supernovae and the host for the paper that you can find on the archive here. Okay, so this is how a Hubble diagram looks like if you don't do anything about it. This is what we call I call the non-standardized Hubble diagram. So this shows that the type 1a supernovae are not always the same brightness. Type 1a supernovae are not natural standard candles, they are standardizable candles. So we can exploit the fact that there is a relation between, for instance, here you see the Hubble diagram showing you the distance modulus as a function of redshifts. This line here is what we expect from H of Hg of Planck, and the point here are all individual type 1a supernovae from ZTF. So this looks a lot like a simulation, but it's not. It's real data, right? And the color you see here are the color of the light curve from the supernovae. And you see that the supernovae that are the reddest are also the faintest. They are way above in the Hubble diagram. So this is how a type 1a supernovae Hubble diagram look like if you don't do anything about it. And what is remarkable with ZTF is that not only we have a lot of points, but you see that up till this redshift of about 0.06, about here, we are volume limited. So you see that we have this line here that cuts the type 1a supernovae like that, like if you were slicing them. This is because we are magnitude limited sample. So above this magnitude, it's not that we don't have the light curve, it's that the follow-up, spectroscopic follow-up from the BTS survey that Dan Perry has presented yesterday, we have this very well-controlled selection effect on the spectra. We have all the spectra up to a magnitude of about 18.5. And this ends up in the Hubble diagram of things that we have all the type 1a supernovae, the volume-limited sample, up to 0.06. This means that this sample below 0.06 is very powerful to study the properties of type 1a supernovae, because this sample of about 1,000 type 1a supernovae, it is this redshift, we just need to look at the data. We don't need to do anything about correcting the selection function. Any correlation, any shape, any distribution we see are representative of what nature made, or what nature provided. We are really a random sampling of the parent population, is what we call it. And when we do that, we see many things. If you focus on this sample here, you see here looking, for instance, at a stretch distribution. So focusing on the right panel first, you see here that the type 1a supernovae stretch, so the X1 parameter here, is very bimodal. So this is what you see here in gray. And this was what was expecting for the last few years. We were definitely seeing very well this bimodality. And we also see that it is depending on the environment. You see that supernovae from locally red galaxies have this double peak here, while type 1a supernovae from blue galaxy have a single mode here. It's something that was predicted before with factory data, for instance, a paper that we led with my students, and we do see that very well independently with a sample from a volume-limited survey. So you see here, for instance, that the supernovae from the low redshift mode here, this mode there, are only present in all population, all environments. So this is a strong confirmation of things that were known now for the last few years, or even a decade. This is confirming that the stretch seems to be connected indeed to the age of the progenitor. But we made something else that no one were able to do before, is to look at the cluster. So about 5% of galaxies in the universe are within clusters. And in clusters, the star formation activity of clusters is very low because the gas went away, and so the star formation happened a long time ago, and so nowadays there is no much star formation within cluster. And when you look at the stretch distribution on average from the type 1a supernovae here, the blue part are the field galaxy, and the orange are the supernovae from close to cluster host. And you see that the closer you go to the center of the cluster, the lower the stretch is, because you are losing this mode here in blue that is only associated to young environments. When there is no more young environments, the average, you are favoring the low stretch mode. So this is a completely independent confirmation that indeed the stretch seems to be connected to the age of the progenitor. And there is something even funnier that we can do here is that we can now use type 1a supernovae to probe the star formation activity at the distance of the center of a cluster, something that cluster people are really looking at because there is a lot of information of the galaxy formation and clustering in there. What was very surprising to look at is that when we look at the starizations of the trip relations, the brighter, slower relation, that's the connection between the phyllid supernovae are brighter when their stretch is larger or slower, used to be assumed to be linear until now in all cosmological analysis. And when we look at the data we have in ZTF, those are all the gray points. If you beam them by stretch here, you see that the supernovae from the low stretch mode here, that corresponds to those guys here, you see that there is a visible break here that you can see from the gray clouds, and that you can see very well in the green beaming. And so you have this broken, what we call the broken alpha relation. We have demonstrated at the 10 sigma level with all those data that we are indeed the supernovae from the low stretch mode don't have the same alpha, so the same brighter, slower relation than the one from the high stretch mode. And the dashed line here is what you would assume if you were to fit a linear line. And so this is a new way we have to do standardization. And it is very clear that we have this broken alpha, and this is changing the way we have to do standardization to do precision cosmology. If we now are looking at the standardization in another way, we can also use the twin. Sorry, not the twin, the siblings. So there are many cousins, the twins, the siblings. So those siblings are the ones that are coming from the same galaxy. And we have a few cases of supernovae that we found to be from the same galaxy. So the interest of that is that you know the distance. You know that they are the same distance. And so if you don't have the same stretch for each for them, you can have a weight on measuring what alpha should be. And if you do that, and if you split them by low mass hosts that are favoring, low mass hosts, yes, here, that are favoring blue environments, so low, high stretch modes, and supernovae from high mass hosts that are favoring all population, this is here, you do see completely independently with siblings that indeed you may have different alpha as a function of the standardization. So that was found independently by those two teams looking at the data in a completely independent way. If we now move to the color, again, focus on the right first, you see that we are, because we have so many data, you see that we have, if we bin all the color distribution from ZTF, this is a gray point we have here. But we were able to divide the supernovae in two subsets of environments, what we call the dustless supernovae. So we define those are supernovae from far from their galaxy in a very low mass host environment. So you don't expect much gas, you don't expect much metals there, so you don't expect much dust absorption along the line of sight of those guys. And then you have the other subset, all the other galaxy supernovae that were not in the dustless sample. And if you do that, you see that the supernovae here in green are favoring this central mode here, the Gaussian center here. And the line here, just so you know, the line here, that's the model, is a convolution of a Gaussian distribution for what we think is intrinsic scatter, that have one mean color and one width of the scatter of the intrinsic color, convolved by an exponential decay that will correspond to the dust absorption along the line of sight. And you see that supernovae from dustless environment don't show a very strong tail, while the other supernovae do show a strong tail. And so this shows that indeed it seems to be that we are able to say that it is correct, that indeed we are dominated by intrinsic color in the center and dominated by dust for the radar object. Another way to see that is completely independently, this is something led by Brody, is that we can do this analysis of measuring those parameters if you slice them per host global mass. And if you do that, you see that here it's indeed the average color, so the mean of the Gaussian, the width of the Gaussian, and the intensity of this exponential tail. And you see that the mean of the intrinsic part are indeed completely independent of the host, and they seem to be flat, while this dust parameter here is significantly different. In low mass hosts, you don't have much dust. In typically Milky Way-like mass hosts, you do have a lot of dust apparently, and when you go to high mass galaxies, where you almost have no gas anymore, you don't expect much dust. So it's exactly the kind of behavior we were expecting if indeed this exponential tail were caused by dust. So again, two different analyses showing you a consistent story that indeed type 1a supernovae color seems to be twofold. A part caused by intrinsic scatter around 0, and a part completely dominated by dust above 0.2. But what is remarkable is that now if you look at the connection between the color of the supernovae and the average magnitude of the supernovae, so the standardized here, but for the color, this is the redder, fainter relation is completely linear. I mean, there is no deviation there. And to me, it doesn't make much sense, because we just spent the last few minutes explaining that there are two regions of the color. There is intrinsic color and there is the extrinsic color, there is the dust. Above 0.2 here, above this line here, you are completely dominated by dust. Below here, you are completely dominated by the intrinsic scatter. But on average, the color magnitude relation seems to be the same, whatever the cause of the color of the supernovae. So I was not expecting that, and I can't tell why it's so. I can just say that for supernovae cosmology, that's pretty useful. But I'm not sure that's enough to explain why we have that. Okay. Let's move on now to the host bias, or the environmental step. So if we now standardize for the stretching color, here accounting for the broken alpha, but even if you don't account for it, you have something very similar. You see that if you look at how supernovae behave as a function of their local environment, you see that you have two clouds very clearly in the gray points, and even more clearly in the beamed orange values. Here you have supernovae from locally blue environments that are significantly fainter than supernovae from red environments, and the amplitude of this step is very big in ZTF. It's about 0.18 magnitudes. It's twice larger than everything that has been seen before, and even larger than when I published something about the size, about 0.15 a few years, 9 years ago, people were like, that's way too big. And now it's like even bigger. So it's about twice larger than what most of the literature have published on it. The consensus was about 0.08. We are more than twice larger. And it's not just because we are taking into account the broken alpha. It happens that the broken alpha is increasing this effect. And one of the reasons for that is that when your model is correct, then the parameters are not trying to capture some other parameter because they are correlated. And so when you are refining and getting more accurate model that represent better your data, then the parameters of standardization are doing their job and not trying to capture something else. So it is very large. It's 0.18, twice larger than what the literature were usually saying. Something else that we see is that the amplitude of this step does not depend on the color of the supernovae. So here I'm showing you, again, the Hubble residual split per supernovae from high mass host in red, or low mass host in blue. And you see here that the difference are blue and red. This is because you have this step between supernovae from massive galaxies and supernovae from low mass galaxies. Another way to show this because they are extremely correlated, color and mass. And it has been claimed that this step were supposed to change. So this is the kind of plot you would see in the literature from Dylan Browns and Dan Skolnick, showing that the step is indeed small in this direction and it's getting bigger and bigger. And be careful, they switch the color. or we switch the color back more because blue galaxy small galaxies are bluer, so we use the blue color. And so you see that they find a very different step using the Pantheon data, while our step in our volume-limited data set of the same size is completely constant. So it's hard for me to explain why they have that, apart that they have to correct for selection effects, they have to correct for more noisy data, but it's not trivial to me. I don't have a clear explanation yet of why they do see that the mass step depend on the environment of the local supernovae color, and we don't. But definitely we don't. This is a claim for them that the mass step were caused by ill modeling of the galaxy dust, and it doesn't seem to be the case for what we have. Okay, so we are not just raising cosmological light curve, we're also raising a lot of spectra. So this is just to show you that we have an amazing data set. It's just pure advertisement. It's showing you the average. It's showing you the average spectra that we are releasing, about 5,000 spectra, as a function of phase for the low mass host, the low stretch galaxy supernovae and the high stretch supernovae. And just to give you a sense, the light band you see here are the expected SOL2 model for those supernovae. And we see that we have a very, very, very nice data set that we are releasing to the community this summer. Okay, so let's now go back to cosmology. And this is a Hubble diagram. And if we account for the standardization parameter I was showing you, this is how the Hubble diagram looks like for ZTF. So it's 2,646 type on a supernovae that follow very well the line here. And if we beam the redshift here, you see this is the gold point here. And the scatter, the NMAD scatter, you see here in yellow, is our typical scatter. And the gray, the black line here shows you your expected 0.15 scatter that we usually find in type on supernovae. So you see that it grows larger at low redshift. This is because of peculiar velocity, as the amplitude of the peculiar velocity is shown by this gray band here. So we typically are reaching the precision with ZTF that we're expecting for cosmology. Now, for cosmology, the heart of the problem is a lot about the photometric accuracy we have. So we know from looking at the light curve residual that we have a pretty good photometric calibration. So this is showing you in this plot the light curve residual in the pool. So this is data minus light curve model divided by the error on the data for all the 3 bands from ZTF. So this is all the points of all the supernovae that enter the Hubble diagram, the 2000 I was mentioning, for the G band, the R band, and the I band. So you see many things in there. It's a very busy plot, so I'll just try to explain what matters. Is that in the phase between -10 to +40, this is where we fit the data, and this is where the model is well trained. And we see that we are roughly fine at all wavelengths. We don't see any shift. We don't see any significant crazy variations. We see unexpected variation at low phase between -20 when the supernova explodes and -10. But this is because the source model is not trained there. There is no training data in there. And so it's not unexpected that a non-trained model don't follow the data. So the ZTF dataset will be able to help training this data. But globally, the message I want to show you is that we have a pool that is about 1, and so we control well our photometry and our error. But well is not enough for cosmology. And we are not releasing cosmological parameter as a part of the DR2 because we are aware of small, tiny effects that will affect cosmology and that we have fixed. But the time that we process the data, the time we do cosmology, the cosmology release will be in a year from now. And this is to show you the strongest effect we have discovered in our data that was blocking the fact that we can use the DR2 for cosmology. So this blurb here you see is a residual to the PSF modeling we were doing for all bright targets, about between 14 to 16. If we do the same thing for the faint target, you see that we have a blob here that is quite strong. And this is because we have something that we've called a pocket effect, which is similar to something called the persistence in CMOS detector, is the fact that you have, when we read out, you are missing electrons that don't follow the readout. And it depends on the flux you had before. And so basically it disturbs your PSF, and this is depending on the flux of the PSF because of the pockets. Basically, it's a complicated model, but we have fixed this model, and so we know that the distortion of the PSF depends on the flux that enters the model. And so you have a nonlinear effect, and this is showing you the effect on stars you have here as a function of the Gaia magnitude on the residual to the average, and you see that it's about a few % nonlinearity that you have here. and a few percent is too much for cosmology. And so it's fine for everything we see. We just barely move the light curve. It will barely move the color because this effect is roughly the same for all bands. But for the 0 point and controlling our error, not only we have this, but in addition, the DR2 is based on what we call force photometry. And so it means that we are extracting the flux by the image differences. And in a difference image, you don't have stars anymore. And so you cannot control well your error modeling. And we need that to get precision cosmology. So just this was trying to show you that we have not yet releasing the cosmology, but you can trust the light curve we are releasing. And why we haven't released so far the cosmology? Because this is our target goal. This is what we call the Lemaitre diagram, not the Hubble diagram. That shows you the same thing as before, a normal Hubble diagram, except that all the supernovae in this plot are completely new. None of them have been used by cosmology before. We have teamed up with the SNIa 5 years and the Subaru team to release this ZTF plus high-Z Hubble diagram that will contain 3,000 type 1a supernovae, a bit more than 3,000 type 1a supernovae, about 2,000, so one from this DR2 sample plus about 800 at high redshift up to a redshift of 1.5. And this Hubble diagram will have everything new. It's very important to do that in our perspective, because as Adam just mentioned, we are in the edge of potential. Something very important for cosmology is that the W0 is different than -1. And it's exactly as Adam said, if it's not exactly -1, it's weird. And we don't know how weird it is, we don't know why it is weird, it has to be -1 or it's something very, very different. It's exotic dark energy and we don't know what that could be. And so the stakes are high. And so this is why we are pushing so hard, because if you see here in adapted plots from the DESY value, from the 1A point of view, you have to compare here the red line, which is the best W0 WA model, that is different than -1, and the dashed line here, which is the Planck expectation for a best fit lambda CDM. And you see that they are anchored here very well at high redshift because you have so much data there. But where deviation comes from is by comparing the high redshift to the low redshift. And so where deviation comes from DESY is exactly a low redshift. It's exactly where we have the ZTF data. And so with ZTF calibrated, we are able to here probe quite quickly if we do or not have a W that is indeed different than -1. And so for that, again, we are doing an entirely new pipeline to redo everything and fix all the bugs we found in the ZTF images, and most notably the pocket effect. But we're also calibrating the throughput exactly of the feature of the system. We are adding Subaru, we are adding a new inference, so we are not we try to do everything new. So new inference for W, new simulation to do that, new data. Okay, moving up a bit more quickly on prospective, what we can do with this data set is that, as Adam mentioned, if you focus on the low redshift sample from ZTF, you see that we are measuring not we are measuring basically H0 squared times the average humidity of the supernovae. And so you need an independent measurement of the humidity to get H0, and this is what Adam just presented to you. We go from geometry, we anchor the pulsation, the geometry enables to anchor the pulsation humidity of the Cepheids. We observe Cepheids in host of type 1a supernovae. This is giving you the average humidity of the supernovae, and you use that in the Hubble diagram. In fact, you do that all simultaneously, but the spirit is this one. And this reaches to about 73, and this is one part of the Hubble tension. What we could do with ZTF is to change that. What we are suggesting is that we have actually right now, Adam, we have about 40 type 1a supernovae that are reachable by TRGB distances with GWST. So the only thing we need is a lot of GWST orbits. But apart from that, we're good. And, but just to show that basically what we are proposing to do is, again, a new way. So we want to do a pure ZTF 1A sample. As I mentioned before, a very good thing that they have made is that they have a pure HST a photometric sample between the calibrator and the geometry for the Cepheids. We want to do the same thing for the 1A. To do that, we want to be, in addition, volume limited in both cases. So I presented that below 0.06, we are volume limited, and we have about 1,000 supernovae already. So that's completely done. Below, if we go up to 50-something, we have already about 40 type 1a supernovae that are reachable by GWST with some time on it. And with this thing, we are self-consistent in the calibration, and this is self-consistent in the photometry, so this is much easier to do relative photometry than absolute photometry. And we don't have any selection function. And the fact that we are targeted for TRGB is that we can do that in any galaxy. And so that's powerful because we don't need to think. And that's usually a good thing. One other thing we can do with ZTF for cosmology is that we can look at peculiar velocity that I told you about before that are very important at low redshift. And you see, we are scanning the entire sky, but for the south part, obviously. And so what we can do here is that the peculiar velocity are probing the density field of the universe because the galaxy, the supernovae will fall in overdense fields. And to get access to the peculiar velocity, we can use the difference between the observed redshift that we do observe as the redshift you expect given the distance of the supernovae that is providing you the cosmological redshift. And by having the distance, assuming cosmology, but here is very not sensitive to any cosmological parameter, we can get the peculiar velocity. And if we do that, it's something we can only do at low redshift where ZTF is probing distances. And you see in this diagram here showing you, for instance, sigma 8 as a function of omega m, using peculiar velocity only, the supernovae we will have at the end of ZTF2, it's about 5,000 type 1 supernovae, so we already have more actually. We have this band here, and this is to show you where we are with weak lensing. It's almost state of the art, I haven't updated the plot. But what is remarkable is not only we have this band here from peculiar velocity, but the usual way to measure type 1 supernovae is that it constrains super well omega m. And so supernovae, if you add on the Hubble diagram, we have something almost vertical in this line. If you combine the peculiar velocity of the supernovae and the normal Hubble diagram, we have this contour here, which is completely competitive with weak lensing. And only with type, and this is only at nearby type 1 supernovae plus a high Z to get omega m. And this is only something we can do now because we have to correlate supernovae spatially to do that. And this requires a lot of supernovae of the order of 5,000. And this is what we are getting now at low redshift. But you see here in the peculiar velocity, this is showing you the amplitude of the signal, basically. It disappears quite quickly. And so above 0.1, there is barely no signal. So this is not sure this is something SST, for instance, will be able to do. So this is really a niche for low redshift sample like ZTF. Okay, how long do I have? 1 minute. So this is a kind of a summary slide that is showing you that ZTF cosmology, we are releasing a lot of type 1 supernovae right now as part of the DR2, and I showed you that we have very strong results for the sterilization part of the cosmology, and this is only to show you the part of the sterilization. There is an entire equivalent set of papers from the physics of the supernovae that has been led notably by Kate's group. Here we can have a strong effect apart from the tiny detail of GWST. On H0, we have access to a new way to use type 1 supernovae to unlock a new way to look at the universe, and we are about to release in a year from now a W measurement fully independent of everything that was done before to see if W is indeed different than -1. In the minutes that are left, is just to show you some perspective of where we are. So this is the DR2 sample I was showing you, and this is this curve here we have. So it's a line to make it nice, but if you plotting the cumulative number of supernovae, it will almost be this very same line. And this is what we are releasing as of today. We are already here, so ZTF, ZTF1, ZTF2, ZTF04 are trying to find gravitational wave as Mansi presented. We are here already that we have on disk, we have about 8,000 type 1 supernovae, about 8 type 1 supernovae that we should have by the end of ZTF4. This is already a lot. 8,000 type 1 supernovae at low Z. That's mind-blowing for cosmology. But we're going to go even deeper than that, is that we have also photometrically typed type 1 supernovae. As I told you, the limiting factor of the sample I was presenting to you is the fact that we are limited in magnitude at 20.5, but we are limited in spectroscopy follow-up at 18.5, so 2 magnitude difference. If we don't require to have spectral typing, if we are relying on phototyping, which is quite strong in ZTF because we have very dense sampling of the light curve, and we do see the second bump in the I band and the R band because we are low redshift sample. This is the quick number we have read together. We should be close to 40,000 type 1a supernovae photometrically typed by the end of the survey, which is arriving in a year from now, not even. So this is a DR3. A lot of work. It was very hard to do the DR2 with 3,000 type 1a supernovae. But 40,000, that should be fine. And with this, so to give you some time scale, we are going for the 2.5, which is really the same thing as the DR2 in the supernovae, but with a new calibration, with a cosmology-ready photometric light curve to reach the cosmology. And we are expecting 2 more years to release all the 40,000 type 1a supernovae to the community. And with this summary slides, I thank you.
you, Mickael. Questions?
Mickael, that was a great talk. Really good. Really good. Just blown away. I did want to ask the differences you saw with Pantheon and BS20 and that stuff. The one thing I wasn't clear about was, I mean, your selection or your survey is all sky, and so you're going to be much more skewed towards smaller galaxies, dwarf galaxies, things like that. Whereas the Pantheon Plus, those compilations are based on surveys that were pointed surveys. So do you know how different the galaxy types are, and whether you're really comparing the same thing, like when you look at a color of a galaxy, whether, you know, for Pantheon, that's, I don't know, a big spiral, and for, you know, you guys, that's some dwarf irregular or something.
Yeah, so that's the thing that we have in ZTF. We don't have any selection function in that sort because we gather everything. The Pantheon plus low redshift sample you're mentioning, I guess the high redshift should be fine because they are similar. But the low redshift sample indeed is a compilation of very complex surveys that have targeted different surveys. And the selection function here has been really a nightmare. So it's hard for me. We know that we are indeed we have more low mass galaxies. We have more low stretch. Yeah, so if you
you could sub-select from your survey as though it was a conventional survey of the past, basically taking the, you know, the well-known galaxies and whatever.
So we haven't. One thing is that I know that, and this is one of the reasons they went to remove them for the latest DES sample that in the DS community, is that it was actually very hard to understand the selection functions they had. So we can try one selection function to try to mimic that. But one thing they concluded is that their selection function is super hard to model. And so we can try to see if we can get close and see, it could be an interesting analysis to see what if what we see that is different is because of their selection function. This is my guess, but we can maybe try to have something more robust than just a guess.
Good. So when you showed your light curves,
yes,
the third one had almost too many points, right?
Almost.
When do you have too many supernovae?
Too many supernovae?
Yes, for the Hubble diagram. 3,000, 6,000, or 40,000? How many?
I don't know. The thing that, you know, when you get rich, you want to get even richer, I guess. It depends for which science. For instance, for W, what matters is not the Hubble flow, because we are overkill already. It's the fact that if we wait longer, we can go for 40 to 50, and this is matter. So we can do much better at low redshift, for the very low redshift, and this is just time. Yes. For the W, I think ZTF, as the size it has right now, is already going to be the leading sample, but the LSST will have hundreds of thousands. So we'll have to have something of a similar scale. So I guess the size will be given by the biggest one. And then for the peculiar velocity analysis, then this is where having a lot of points matters, because you can correlate that. And the more you have points, the different scale we are probing. So if you have 10 points, then you see a very long distance. If you have 1,000, then you see very small distance. And you don't probe the same physics. I'm not so sure.
Yeah, one comment actually following up on you know, your answer and your question. I mean, the nice thing about having 40,000 is then you really can, you know, divide in zillions of subsets, testing all the type of host galaxy properties. And we will need that to compare with the high redshift, where things will be changing. So we need to figure out how sensitive we are. Yep. So I think the 40,000, we'll use them. Don't worry, we'll use them.
Yes. We already have them. We know what to do with that.
Very good. Christopher.
Yeah, I guess with this many supernova, you can also start thinking about turning all the analysis to 2D, basically. Can you talk about, do you have plans for this H0 in, you know, for every pixel? Every
yes. So for H0, this is something indeed you can do. For W, it will depend on you need to have this at high redshift too. So in the LSSC era, yes.
Very good.
Thank you very much.
Thank Mickael again. And we have half an hour for a coffee break. Is ready to tell us about building a UV-enhanced Hubble diagram. Please.
All right. So thank you to the organizers for giving me the opportunity to speak here. No, you don't get many thanks for actually placing me directly after Adam's and Mickael's great presentation, because mine will, I think, not be as impressive, but it's something we can do, and I wanted to run it by a bigger group to actually get your feedback, whether this is and actually, of course, then if it's a good idea, actually do it. So the idea is that we enable the UV to help us in actually building better Hubble diagrams. And so let me go through how this works. And I'll start essentially by just a mini review of UV observations of type 1a supernovae. So of course we all know UV is just observable from space. So currently that limits essentially the instrumentation to HST and Swift. Now supernova, it's as if that's not complicated enough. Also in the UV, supernova 1As are very dim, so you have to spend a lot of time. As a result, for instance, Swift UVOT is only going to observe supernova up to a redshift of 0.02. So just not enough to actually put them on the Hubble diagram. HST can go deeper, but of course HST is also very expensive. So accordingly, there's really not much UV data in the Hubble, for supernova in the Hubble flow, and people have essentially omitted it from cosmological studies. And the question is, can we change this picture? And the answer is, of course, yes. Otherwise, I probably wouldn't have raised that question. But and the first element is essentially that we are building a wide field UV imager here. Called Ultrasat. The name came up a few times, but I'm not sure if actually the picture of the satellite itself has been shown. So this is a collaboration between Israel and DESY. So I should have said DESY is my host institution. It's a national lab in Germany. I'm being so explicit here because you actually find exactly those 4-letter combination now also in the context of Dark Energy Survey Year 5. So this is a different thing. It was difficult enough already when it was DESY, DESI, and it just got worse because of Year 5. So this is an institution, and we are in charge actually of the camera for Ultrasat. So that's 90 million pixel CMOS device that we are just right now putting together, and it will be. The charm of Ultrasat is, of course, its huge field of view, 204 square degrees, so that's more than 4 times the size of ZTF. I don't have one of these great pictures where you see the field of view, but you can imagine how it looks like. And then, that's key element number one. The second is the wavelength range. It's between 230 and 290 nanometers. That's where we are sensitive. And, this is the total throughput that you're seeing here. Parts of this, actually all the parts are already verified in the laboratory. So we've done on Scout of the CMOS and at DESY, we have done a QE measurement, so we can actually show that we can achieve what we need, and so we are confident in the throughput of the system. Okay, so this is Ultrasat, and of course the science is everything from gravitational wave astronomy over supernovae up to cosmology. So the sensitivity is shown here in the diagram that, what is this? It's only cut off here on this screen. Okay, so this is, you've seen the same metric already here in the talk of Mansi, so it's called GRASS, the volume that one can survey as a function of time. And now this is evaluated only for hot sources. In the UV, you're of course sensitive to hot sources, so above 15,000 Kelvin, everything in a sense, you're just in the Rayleigh-Jeans tail. And all sources look the same then, so you can compare something in the UV to that in the optical, and that's why you can actually plot the GRASS as a function of wavelength, and you can compare Ultrasat here with other missions. If you compare it to GALAX, the previous experiment, you see it's almost 3 orders of magnitude more sensitive, so that's great in terms of discovery space. But also, if you compare it horizontally, we have the sensitivity of LSST for finding blue transients. And so essentially, and this mission is dedicated to finding blue transients. So we will also be able to dedicate a lot more time. So I think you understand where we are getting to. So, we want to actually find, in particular, also kilonovae, but we want to also find lots of other things. And so the survey is essentially right now designed, and this is how it looks like. So we've essentially decided on how to split the time. So there's the largest chunk of time will be dedicated to a high cadence survey, so 204 square degrees on with a 5-minute cadence, but also 3 hours a day will be dedicated to an 8,000 square degree survey with a 4-day cadence. So that's the survey which can deliver a lot of interesting data for 1As. And then there's TOO. So just to give you a sense for the sensitivity, so for a kilonova similar to AT 2007 GFO, we would be able to see such an object up to 240 megaparsecs. So we'd be surveying a volume of 0.2 gigaparsec, and as a result, we think that once Ultrasat is being launched, we'll see hopefully more than 1 kilonova per year. Hopefully by that time that the field can move on. Other things that Ultrasat can do, and I'm just naming one, TDEs. We find thousands of TDEs per year, and depending on redshift evolution and temperature, even up to redshift of 1. So there's a lot of things Ultrasat can do, and I'm just giving you here a list of the different working groups just for information. Anything from transient stellar explosions up to exoplanets, stars, galaxies, AGNs, TDEs, and so on. All of this is covered, of course, gamma ray bursts. I will focus today on cosmology, and only just one aspect of cosmology, namely building this Hubble diagram. And so we've seen this plot. I don't have to introduce it, fortunately. And the point, I think, which is important is that supernova are still key in making these dark energy measurements. And you see it because there are 3 different supernova samples, and the whole ellipse is moving around pretty significantly. So that doesn't mean that there's anything wrong with the supernova. It just means that the supernova is a sensitive part in this combination of data. And so if we want to really understand, essentially, is W evolving or not? Are we seeing a changing dark energy? We need to become better. And already we've seen sort of Mickael presenting plans, but we should be thinking hard about how can we make sure that this claim is becoming right. And so this, as Mickael showed, a similar but much fancier distribution. It's essentially how much is the distance modulus changing, in fact, if W is truly variable. And this is just something I did for myself to understand what do we need as a target. And we need to be, get it right to roughly 1%, maybe a little bit better. And that requires calibration, but it also requires that we can control for supernova evolution. What we've discussed yesterday was, of course, that supernova 1As, that's a pretty diverse bunch, even if they don't look like it. It's how the different progenitor systems are looking very different. It's kind of naive to assume that they all have the exact same brightness. And so they will be diverse. The question is, does the diversity composition change as a function of redshift? And that is if it were, we could be expecting that there's also a shift in the magnitudes that you derive, and as a result that one can easily get it wrong if one does not account for it. Okay. So how to do this? Well, I guess we've seen this also from Mickael already. This is just how to standardize supernovae in the optical. We all know this. There are ways to improve, but then you need to have specialized information. We've seen, I think, from in the both previous talks, it's mentioned twins. So there you need good spectral information. We might not have. We actually don't have this for high redshifts. We have it for nearby redshifts, but also with the near UV information, you can actually improve the dispersion. And improving the dispersion is quite nice because, not for the statistical arguments, but it means you are actually sensitive to population effects. Because that in a sense, you're correcting for these population effects. And as a result, your dispersion becomes smaller. But just the fact that you can means you have an extra handle to constrain evolution also. Okay, so, how does the UV sort of come in here? So what you're seeing here is essentially the UV spectra between for just 10 HST observed supernovae, and they all agree nicely sort of in the optical. But then when you enter the near UV and the regular UV, it actually becomes pretty dispersed. And so, for instance, here, this can be used already to improve the distance, the standardization, but there are more features. And so there's a lot that this diversity can tell you about the progenitor and the, whether it's single degenerate or double degenerate. And so that's just useful information. The other bit of information, of course, is dust. The UV is extremely sensitive to dust extinction, and roughly a factor of 3 more than the optical. So if we want to understand, is the dust done right, it's helpful to actually have the UV as an extra level. So the idea is not to actually replace the optical bands, but the idea is really to just amend the optical bands with the extra UV information. And now, unfortunately, if you test it, if we wanted to see, can we, how sensitive are we? What can we gain? Can we run our usual simulations? We realized nothing that we are used to kind of works because the UV, in a sense, is so underexplored. And so what you're seeing here is just the SALT template, SALT 2.4 and 2.3 in the ultrazard wavelength range. And you see these spectral templates, they don't make any sense because they simply have not been trained. This is just for you to understand where we are. I mean, it's so this is not meant to, and this is just showing you how big the problem is. So how should we go about? I mean, it sounds like we have almost nothing. The truth is, the nearby that's the harder part. The high redshift part is actually simpler. And the reason is, if you can go deep, then of course the light that is emitted in the UV will fall into your detector in the optical. So if you, let's say, take a redshift 0.9 supernova, that light will that light, the UV emitted light in the ultrazard band will be falling right into the G band. So that's nice. The same trick you can play for the U band. Then you move even closer. So at redshift 0.34 will fall into the U band, and so that's actually pretty accessible. So in a sense, we can take UV observations with existing surveys and with future surveys like LSST without a big problem by just making sure that these bands G band and Z band, G band and U band are available. And so we did this for SNLS, and we checked for do high redshift supernova from SNLS, do they show emission in the rest frame UV? And the answer is yes. For roughly 1/3 to maybe 50% of all supernovae, we actually did find a 3 sigma data point, which means that it confirmed that there is signal to look for. It wasn't quite enough to do an interesting cosmological study, but it allowed us to actually make some firm prediction in terms of rates. So we think that ultrazard will be actually, be able to find up to 3 or more than 300 supernovae per year, up to a redshift of 0.1, and actually 2,000, more than 2,000, up to a redshift of 0.2. So this is what ultrazard can deliver. And then if one would match it to higher redshift, then we can actually we can use the same kind of UV information also for high redshift supernovae. And so this is just showing you how the DESY, oh, sorry, this needs to go here. Where is this? Anyway, it's maybe not so important. It's, the blue points are just from the dark energy survey, and the orange one here are from SNLS. And this is sort of an inverted Hubble diagram. And it just shows that already there is sort of UV data at high redshifts available, but we should get a lot more. You can see the same thing here also now for up there, G band, I band, R band, and then upper left, that's the U band. Now in the U band, there's absolutely no data, but it would be actually quite easy to get. So, if we would just use the U band, for instance, in connection with LSST, we would start being able to populate that upper left diagram. You're also seeing the SNLS curves, the SALT curves, and you're seeing how unconstrained they are. And so actually putting some starting to constrain that could actually lead to much improved standardization, we think. Okay, and so this is how a Hubble diagram could look like if you combine everything. So for the lowest redshifts come from ultrazard, and then the Rubin LSST with U band could then provide this redshift bin. The G band would provide this redshift bin, and then Roman, of course, can go much further if just a sufficient blue filter is being added. So this is how it could look like. In principle, there's nothing to stop us. And with this, I conclude. So Ultrasat will enable the observation of UV light curves for hundreds, perhaps even thousands of type 1a supernova. And if you combine this with optical information and maybe infrared, we could actually get an extra lever for understanding the objects and put some systematics into it. Okay, there's a lot of astrophysics, explosion models, and so on. But we need to combine it also with a high redshift survey and make sure that we have the complementing data at high redshift. And here, I think there's lots of room for collaboration. And if you're interested, just talk to Jakob Nordin or myself, and we'll see if we can do something. Thank you.
Marek, questions? Ariel.
Thank you, Marek. When you say that there will be discoveries, you said like in the hundreds or even thousands, how well measured will those be?
I think they will be quite well measured. At least those up to a redshift of 0.1. So if you compare, and I didn't talk about this, but if you compare the sensitivity of, let's say, SNLS to or even if the flux of a redshift 1 object observed with if you translate our observations with with SNLS to what we would expect with ZTF, you do the refraction of distance modulus and so on, you correct for distance. It turns out that it's equivalent to a redshift 0.25 supernova or so. So if we would be observing a supernova at redshift of 0.25 with Ultrasat, we would get a similar light curve as SNLS had, and at redshift of 1 or 0.9. So that means to me, if we actually go to redshift of 0.1, we will have fantastic signal to noise. We'll have a 4-day cadence, and I think we'll get pretty nice light curves.
But for the UV light curves, you also need the optical light curves.
Absolutely.
Where do you get them from?
Well, that's why I'm here. Yeah, I mean it's but it's not like people are going to hopefully. It's not just for supernova, right? For for 1As. I mean, we want to continue with ZTF. We want to continue with LS. We will have LSST. We will have LS4, but it needs coordination. I think we're not going to set up our own survey, yes.
Clearly. Mickael, you get the last question.
So will Ultrasat be full sky like Galax was, and you go back to the same place of the sky regularly, like every 2 or 3 days, or?
Yeah, yes. I mean, it will be 8,000. No, not full sky. It will be 8,000 square degrees in the north and the south, and we'll be going from one to another, and so there will be sort of 2 surveys per year on a footprint of 8,000 square degrees.
Great, thank you very much.
Yes. Just needs to...
So the next talk is going to be about gravitationally lensed supernova. That's going to be on personal computer, and you will understand why very soon.
I love this introduction.
That's a good introduction.
Yes.
Nikki, please. Yes.
Okay, great. Not as smooth as I hoped, but it seems to work now. Great. Hello everyone. So I'm a postdoc here at Stockholm University, and I'll talk about lensed supernovae. So let's start by sketching the setup of these gravitationally lensed systems. So we have an observer, a supernova explosion, and then along the line of sight, there can be a massive galaxy or galaxy cluster that acts like a lens. So the gravity will magnify and bend the light rays coming from the supernova such that we see multiple images of the same object. And we will also see these with a time delay between the images because the light travels a different geometrical and gravitational path. And since a supernova is a transient source, we can use that to measure the time delay between the images by looking at the offset between the light curves. So this time delay is the first ingredient if we want to use lens supernovae to calculate the Hubble constant. The second thing we need is a model of the gravitational potential of the lens galaxy and also the contribution of the line of sight structures. So when we combine these two things, this gives us an absolute distance measurement of the time delay distance. And this can be used to constrain the Hubble constant in a way that's completely independent of the CMB and of the Cepheid calibration. So this is great. However, lens supernovae are very rare because you need to have this exact alignment between the supernova and the lens. So we have found some lens supernovae, not that many yet. So I'm just going to flash all the supernova discoveries, lens supernovae discoveries we've made so far on this diagram, where we have the redshift and the maximum time delay between the different images. Okay, let's start. We have supernova Roestel, then IPTF 16GEU, or 16GEU for short. Then we have supernova Requiem, C22, supernova Zwicky, supernova Hope with H0 PE, and supernova Encore. And you see also that supernova Encore is just a copy of supernova Requiem, because this is actually a lensed supernova sibling, so occurring in the same host galaxy and then being lensed by the same galaxy cluster, which is quite remarkable. Now, if you look at this diagram, you see that there's a wide spread in properties, especially the time delay. It ranges from a few hours for supernova Zwicky to 20 years for supernova Requiem. So we're still waiting for those last images. And what you also see is that there is a separation between two populations here. So we have these ones, which are supernovae lensed by single elliptical galaxies. And then we have the blue ones up there, which are lensed by galaxy clusters. And the properties are quite different. The galaxy scale ones have shorter time delays and are at lower redshifts. And these have all been discovered by ground-based surveys, while the cluster lens supernovae have all been discovered by space telescopes. Now, two of these objects were good to measure the Hubble constant, so we have two measurements so far. The first one was supernova Roestel, which gave a low measurement of H0, and then also recently supernova Hope, which gave a high measurement. So we haven't really solved the tension yet, but we're getting there, and this is a really promising start for a lens supernovae for cosmology. So today in this talk I will focus on supernova Zwicky, because this is an example of the most extreme ends of the galaxy scale lens supernova population. And I'll also talk a bit about what we can expect for lens supernovae in the future. And we will do this by having a nice zoom in into the data of supernova Zwicky. So we discovered supernova Zwicky here with the team at Stockholm, and we took lots of nice observations, so it's going to be good with this screen. We start with the data from ZTF. So here you see the field of view of ZTF. And then we are going to zoom into the quadrant that contains supernova Zwicky. And supernova Zwicky caught our eye. It's this one over there, because it was exceptionally bright for its redshift. So then we did follow-up observations. This is with a very large telescope, with the Hawkeye instrument. This is supernova Zwicky, still not much to be seen. Then we also had observations with MUSE. And the great thing is that this is an eye of view, so every pixel here is actually a spectrum. And this allowed us to determine that you see these two blobs here. The red one on the top is the host galaxy of the supernova, and the blue one is a combination of the lens supernova with the lens galaxy on top of it. But we still don't see the separate images of supernova Zwicky. For that, we had to go even deeper with observations by Keck. And that finally allowed us to see the beautiful structure of supernova Zwicky. There in the top, you vaguely see the host galaxy as well. And this also allowed us to calculate a lot of properties about this lensing system. And we determined that it's extremely compact and the lens galaxy is very light. And especially if we compare this to the population of galaxy scale lenses, they're very different in terms of their stellar mass and their Einstein radius. So if we take supernova Zwicky and 16GEU, the other galaxy scale lens supernovae, then they really seem to form a new population of very light lens galaxies that we could only discover because they happen to be lensing standard candles. So it's great we're finding this new population, but these also tend to be systems that are very highly magnified, symmetric, and have very short time delays. So Anna calculated the time delays for supernova Zwicky, and she found that the best fit time delay was less than 1 day, which is also quite remarkable. But yeah, if you want to do precision cosmology and you have an uncertainty of like 2 days on your measurements, then this is not really going to be good enough. So the same for 16 GEU. Hubble constant measurements, maybe they're not great for that, but we can still learn a lot about the supernova and the lens galaxy itself. So here you see results of the spectrum of supernova Zwicky, which is compared to a low redshift supernova spectrum, and you see that they really have a comparable signal to noise. So this allows you to compare whether high redshift type 1a supernovae are similar to low redshift ones, and they seem to be indeed, which is very important cross-check for supernova cosmology. Another thing you can look at is the lens galaxy. So here I'm going to present some new and preliminary results of a project that I'm working on with many people that are also here today. And the goal here is to constrain the mass slope of the lens galaxy and also the fraction of dark compact objects from these flux ratios of supernova Zwicky. So as I said before, the host galaxy of supernova Zwicky was offset, so we don't see strongly lensed arcs from the host galaxy. And this makes it more difficult to do the lens modeling because we only have these image positions to work with. So it means that we don't have enough information to meaningfully constrain the slope of the lens galaxy. However, there's one advantage here because supernova Zwicky is a standard candle. And we can also use this because we know the intrinsic luminosity, so this means we can calculate the absolute magnification, and this scales inversely with the slope. So this gives us another way of estimating the slope for the system, even though we're missing these host arcs. Although there's a problem with this, because if you do this, you basically assume that all the magnification you see is from the macro lens model, so from the whole galaxy. But when we look at the observed fluxes here, and we compare them to the ones that we model with our best fit lens model, they do not agree. So we predict image A to be the faintest, but it's actually the brightest. And we also need some extra magnification for image C. So one thing that could explain this is that instead of having just this global macro lens model that magnifies all the images also have contributions from stars and other compact objects that are located in the lens galaxy and that each have additional lensing effects. So here you see simulations of these microcaustics for each of the images, where the color corresponds to how much magnified or demagnified you are. And then depending on where the supernova is located within this network, you get additional magnification or demagnification. And when we look at the distribution of magnifications that this can cause, you see that the spread can really be up to a magnitude, so quite large. And this is then also able to explain the flux ratios that we saw from supernova Zwicky that were inconsistent with our macro lens model predictions. So these simulations are made by Luc Weisenbach, and he made them for a range of different slope values and fractions of compact objects. And by assessing all these simulations, we can see what is the most likely slope value of the lens galaxy, and also what is the fraction of compact objects that we need to create the microlensing that best fits our observations. And when I talk about this fraction of compact objects, this is mostly, of course, the stellar mass fraction that we have, but there could also be a contribution from other dark compact objects that we don't see in the photometry. So this could be, for example, stellar remnants or brown dwarfs, or something more exotic like primordial black holes, which we haven't observed yet, but this could be a way to probe that in these low mass lens galaxies. So what we did is we made here the posterior and the likelihoods, which mostly contain the stellar mass estimates, observed magnification, microlensing distributions, and also a prior to make sure that the compact fraction is not above 1. And then we sampled the slope and the fraction of dark compact objects to see what was the most likely values. So let's just do a little bit of a raise of hands here. So who thinks that we would need more dark compact objects to explain the flux ratios of supernova Zwicky? Raise your hands. Okay, I see some hands definitely. And who thinks that we can explain this by stars alone and there's no need for any other dark compact objects? I would say, yeah, divided, half-half. Okay, so here I'm going to show you the preliminary results, which actually shows that stars are enough to explain what we see, and there's no need for any additional dark compact objects. Maybe a bit of a shame, but at least we can put some upper limits. So here we see that the fraction of dark compact objects is constrained to be below 0.5, around that. And we also get the measurement of the slope of the lens galaxy profile, which is about 1.84, which is actually similar to what 6-in-G EU had. So summarizing this for Supernova Zwicky and 6-in-G EU, both of them are light lens galaxies with extremely short time delays, very highly magnified, and they have lens galaxy slopes of around 1.85. And we also have seen no hints for any additional dark compact objects. But these two systems are kind of extreme, and it may be that they're only the tip of the iceberg of what we can see. Because Anna did simulations for what we could expect in 5 years of ZTF data, and she found that if you only look at these very bright systems, like Zwicky and 6-in-G EU, then indeed we only expect to discover one in the whole duration, which is also what we found. But if you also look at the fainter ones, which should still be visible in the data, then you would expect another handful of them, which may have been there, but we could have missed them. So this motivated an extensive archival search by Alice, where she went through the last 3 years of ZTF data, imposed a lot of cuts, and looked if we can see some of these missed lensed supernovae. And she may have found some. So here we have two systems that pass all the cuts. They have DESY redshifts of 0.24, and if you model their light curves, they're actually better fit by multiple light curves than just one. And if this is true, then these would be lens supernovae with time delays around 20 or 30 days, which is exactly what we want for cosmology. So this is great, and it's also crucial for next year, when hopefully LSST will start, and we will have a lot more data with lens supernovae that we really need to filter. So the predictions are that Vera Rubin will discover many, many more lens supernovae. And the question is, okay, how many more is that? So to investigate this, we made simulations of lensed type 1a supernovae, including microlensing, and we computed their light curves, and then also the exact observing strategy and the cadence from LSST to see which ones would still be detectable and which ones not. So the numbers that we get from this are that we expect to find per year around 44 lensed type 1a supernovae. And I mean, this is almost one a week, which is pretty crazy compared to what we have now. And this is only for the 1As, not even the core collapse. And not all of these will be like Supernova Zwicky. If you look at the ones that have larger time delays than 10 days, we will still find around 26. So these numbers are very promising. And if you imagine having all of them on this plot and like really filling up the parameter space, hopefully discovering some systems that will fill in some of the gaps here that are galaxy scale systems with larger time delays, more useful for cosmology, but also a simpler lens modeling than the clusters have, this would be really, really promising. And of course, at the same time, we will still discover many of these supernova Zwicky-like systems, which can teach us a lot about this unexplored population of low-mass lens galaxies, microlensing, and of course, the magnified high-redshift supernova explosions themselves. So I think the times are really promising for lens supernovae, especially with the Vera Rubin Observatory coming online soon. And we're only really at the beginning of the potential of lens supernovae, and we'll discover many, many more objects in the coming years. Thank you.
Thank you very much. Finally using... Okay.
Yeah, I think so, yeah.
And we are getting to the final talk, hints and challenges in supernova cosmology by small parameter. We have the talk. Yes, we do.
Yes. So I was interpreting the title and the request from the organizers that I should be trying to sort of place the afternoon's discussions into some historical and future context to send you off into the world, you know, feeling charged up. And of course, I think you'll see that I captured, I think, a lot of the things that people were saying, although I think what I did not capture were the pretty graphics, especially the last one. So you know, the graphics will be low tech, but hopefully the idea will send you off, you know, in good mood. I was thinking about the question of where are we now with respect to where we had been and where we expected to be at this time in our approach to these cosmology questions with supernova. And I was thinking about the fact that just 6 months ago, I was involved with this Union 3 compilation paper that came out where we went up from the early 50 supernova we all had back when to the over 2000 that we're now looking at, and as one might expect, this wrong direction. This data set was starting to allow us to look at the various different measurements that we have not yet discussed at this meeting, brought together. And what we were starting to see now 6 months ago, this came out, this was in the paper that we submitted then, was this this sort of slightly surprising tension that we're now all been discussing for this I guess the second of the tensions with lambda CDM that we're discussing today. And this particular result, we said it as a very how do we describe it? I guess it was described as a hint and a weak tension. And we commented that we were looking forward to seeing what happened as the EAO work came in, which we were expecting at that time. And then, of course, now just a month ago is when we first saw these graphs that we've all looked at today, where what I think is worth pointing out is that the tension with lambda CDM could have been anywhere in the plane, but it turned out to be in the same direction that BAO came in as the supernova came in. So therefore, what was a 2 sigma-ish effect went up to something that could be as high as 3.9 sigma tension, depending on which of the supernova set you use. So that is actually a number which is a very rare probability that you'll get that by random fluctuation. But nobody gets really excited because we think of this as most significant physics results. You need something that's more 5 sigma, 6 sigma, and that's because we don't actually consider these to be the probabilities. We consider these to be the raw probabilities before you consider systematics. So clearly, we're all now back at the what I was going to say now is that we're now. What was interesting here, though, is that we're now beginning to start to talk about something that we had originally discussed back in the early 2000s, which was what would it take to be able to begin to differentiate between the different dark energy models. And I remember discussions back then with other theorists where we were looking at the differences among the dark energy models that were out around that time, and realizing that the amount of the improvement that we were going to need to be able to trust a new result was tremendous. I think we had to get something like 20 times better in our accuracy, not just statistical, but systematic. And it was pretty clear that it was going to be a number of years to do that, during which every result we came across was always going to look consistent with lambda CDM, just because the error bars would be big enough. And I could easily imagine at that time concluding that, well, people get tired of looking, and they all assume that lambda CDM was the right answer, despite the fact that lambda CDM is actually a rather strange model. And there are all sorts of reasons that you might want to look for something more like a quintessence model. But until now, we haven't had the real opportunity to consider such differences from lambda CDM. But I'd say what's new today, and that one thing that we've all sort of practically take for granted now, after we've seen all these beautiful plots of the day, is that now we're actually able to begin to talk about differences. And so in 2006, what was put forward by the Dark Energy Task Force, those you may remember, as stage 4 measurements, were ones which would be able to give these kinds of contours on a W naught versus W, in this case pivot plot, so that we can start looking for time varying dark energy. And the proposals that were out there for when different stage 4 projects would start, it was pretty clear that the BAO was going to be the one that could come in first, at that level. And in fact, DESY is now starting to come out with results that start to look like these kinds of constraints. Now, I should comment that we are, as I said, we're seeing this, but if you put this on the same scale, it's actually not yet quite as small as the inner contours are that we were talking about for stage 4. But that's just the first year of DESY, and for example, we already know that they're planning to unblind internally the 3 years of DESY just this summer, I believe. So we're expecting within the year to be getting something that might be stage 4 from the BAO side of the world. Now, I think that from the supernova point of view, it's pretty clear that we are now already getting statistics that are in this, are good enough to show these kinds of tensions. So we're thrown back to where some of us were 25 years ago, when we were trying to decide what we believed about the deceleration and then turned out acceleration of the universe, where almost everything depends on how do we manage the systematics. And so I think that in all the work we're seeing, where all the numbers are getting huge, and the question came up, what do you do with 40,000 supernova? It's not the 40,000 that are helping you on statistics that we're interested in anymore. I think we'll bottom out at our systematics at this point at probably a few thousand, not anything like the 40,000. But I think, as Ariel had pointed out, what we're interested in here is using the large numbers to help us with systematics. And so really the question we should all be asking is, what are all the different parts of the systematics left over that we are now going to try to really work on hard? And I know many people in the room, including that I was picking up from conversations over lunch, are thinking about many of the same things that I'll be describing here. So maybe this becomes a summary of also the lunch conversations, as well as the conversations here in the room. So why do I think that this is a time of optimism? That I think that systematics is hard. Systematics calls for all the best creativity of the scientists, right? Because you have to not only invent the solution, but you also have to invent the problem when you're worrying about systematics. So you have to figure out what could be throwing you off, not just how you're going to solve the one that is throwing you off. But I'm going to go for optimism today, and I will argue that we're going to need bottom-up systematics control, and we'll need top-down systematics control. So by bottoms up, I mean we're going to need to be able to understand the calibrations of the photometric systems. We're going to have to understand the calibration of the supernova. We're going to need, and then the top-down side, we're going to have to really understand how do you put a analysis chain together in a way that doesn't introduce biases, in itself. I've been thinking about this, just giving examples from work that I've been seeing close up. But almost every one of these topics that I'll be talking about right now are ones where there are other groups that are doing other work as well, which is also part of the optimism here. So let me just describe a few of these in a little more detail, just to give a feel for why I think there's progress that will be made. Beginning with the calibration of the photometry systems, and there I'll just describe the fact that now there've been several attempts and several jobs done on bringing together the multiple data sets. This is from our recent Union 3 work. So this is David Rubin's very extensive effort leading this, where he was able to simultaneously fit all the photometry systems of all these different searches and follow-ups. And it's interesting to do because you start seeing that it's clear that there are pushes and pulls between all these different systems, such that you can infer that various different filter systems had slightly drifted in their central value and in their widths from what you might have thought their 0 points were ahead of time. So it's not something that you can take lightly. You actually have to do this. It does make you kind of wish that we all had the capability of scanning every filter every night and the entire throughput on these systems. And in fact, I guess if at some point if that became necessary, that would be doable. And there are efforts to think about that as well. But this was already sufficient for that level of statistics. There's the calibration of the photometry systems themselves. So this is work that's happening in several different groups. The one that I've been closest to is the work going on using the 88-inch on Hawaii with the Scala system. And the picture there is Daniel Kuster, who's in the Marek's group at DESY. DESY, DESY. And working with, and Greg Aldering has been leading this work. This is something where I think it may be the first to, out of the box, showing a rather impressive ability to get a first calibration down to within 4 millimags over 100 nanometers for the entire wavelength range from 450 to 900. And that was with just the first round of Scala. It's now been substantially upgraded, and so including other things, it has now 18 different mistraceable photodiodes on each of these 18 different beams that we divide the aperture up into. And unfortunately, there's been bad weather ever since and other problems of that sort ever since the upgrade, and so we're waiting with bated breath for just some good nights of good weather to see how much improved this over this 4 millimag number has gotten. But this will just be one of, and I think there's probably 3 most interesting ones that are coming out, including the Paris group has the two different approaches that they're working on, and we'll get a chance to combine them all together and compare and see whether or not we're getting good systematics on all sides. But I think this is showing that this is a doable job. We can do photometry calibration, and in this case it's spectrophotometry standards in the sky that can then be used in any other telescope in any other project. All right, so that's the calibration there. Then we turn to the calibration of the supernova themselves, and there's a number of different approaches to this. We've been working now for a little while on this idea of twins work that you've heard mention of. I'll just say that if you look at the time series of spectra, these are coming from some 300 time series that were developed by the Supernova Factory over the years. Well, I'll say a couple of things I was going to comment here, but I guess the main point I want to make on this to start with is that if you look closely at the spectrum, I'm going to use this fancy pointer system, at peak here, it's very clear that this time series looks different from, let's say, the peak of this time series. So it's obvious that supernovae are not all identical. What I like about these plots, though, is these show 6 examples of time series that are all not identical to each other. However, each one of them is a pair of supernovae that are great matches to each other. And so the top right panel, there's a green plotted time series on top of a black plotted time series, and you can see they are almost on top of each other. The middle one that I'm showing here at the bottom was a red time series on top of a black time series. And so clearly there are subgroupings of type 1a supernova that are not identical to each other, but come in clumps, and that you can actually be comparing likes to likes if you do this correctly. This particular work was done with entire spectral time series, which you can think of as being a CAT scan through the supernova exploding star, because first the outer layers become visible to you in the spectrum, and then they expand, become transparent, you see a little deeper in, they become transparent, and you see deeper in still. So it's very hard for a supernova to hide any of its behavior if you have a spectral time series. And what we found is that there are in fact these twins that, as mentioned in the earlier talk, the well-measured twins down here have a much tighter dispersion than the poorly measured twins up here. And that was the original result from Fakura that was mentioned back in 2015. But since then, there's been substantially more work, in particular Kyle Boone, and then later George Stein, have used machine learning techniques to visit these supernovae and pull apart. Essentially, they both independently found that a 3-dimensional nonlinear parameter space does a very nice job in being able to capture all this diversity of the spectral features. Now, these were done now both for the entire time series, but also you can do, even just at peak, you can capture this entire diversity. So a peak spectrum is good enough to do this now. And depending on where you are in this 3-parameter space, there's a magnitude that goes with it. an absolute magnitude, so that you can actually treat these as a 3-parameter index into what is the distance modulus that you will infer from a given supernova using these corrected absolute magnitudes. Let's see, the entire data set is now available for anybody else to train your own models. You can see a website up there. But what I want to point out is that this using this form of calibration can dramatically improve the dispersion of the supernova you were seeing results earlier that went down from, let's say, 0.15, 0.16 down to 0.12 or something like that. But you can go all the way down to something more like 0.08 or 0.09 magnitudes. So it can be as much as a factor of 4 in the statistical strength of the supernova if you do this. But as was mentioned also earlier, we don't really care in this case as much about the statistical strength as we do about their systematics control. So that if you can bring the dispersion from 0.15 of what's essentially unexplained dispersion, down to something more like 0.08 or 0.09, there's much room for evolution to happen in the supernova populations if that's your current constraint. And already you can see a difference. For example, the mass step before you do this correction shown in the upper plot, and then after you do this correction shown in the lower plot, and you can see that it can reduce it dramatically. In fact, it could be statistically insignificant. It could be the mass step left over. That's still to be determined. But it is obviously reducing systematics, as you would like to think that the supernova itself could tell you, whether or not it's well matched to another supernova. And you shouldn't have to depend on knowing what its host galaxy environment is. All right, so that I think is a part of this bottom-up element of the calibration. Now, the other point I wanted to make about was this top-down issue of systematic control, that we have to do a good job with the entire analysis chain. And David Rubin, in this particular Union 3 paper, also used a updated hierarchical Bayesian analysis that's called Unity 1.5. And as hierarchical Bayesian analyses always do, they have to show you a directed acyclical graph because that's how you know they're hierarchical Bayesian. But it also begins to capture the fact that you're keeping track of many parameters that describe the data sets, some of which are externally used, but some are basically nuisance parameters. Like, for example, what are the various different cutoffs of the different surveys that you were putting together into this work, where they're coming from, and then it does provide you ways to check that those parameters are well fit by looking at the posterior expectations. And so, like these plots here on the right side show you for many different of these surveys what the posterior prediction was versus what the actual data set looked like for where the cutoffs would be for the magnitude distributions, just as an example. But you can do that for many different parameters and get some sense of confidence. But the thing I thought was pretty interesting for this hierarchical Bayesian analysis that is worth probably remembering for other purposes as well is the fact that you're keeping track of all these different nuisance parameters simultaneously when you do these fits, and this is important because what we've studied earlier, and this is from Samantha Dixon's 2021 paper, is that when you sequentially correct for different effects in a data analysis chain, but don't keep all of the correlations between the different hidden parameters, you can easily introduce biases if there's some correlated nuisance parameters in that chain, and many of the other analysis chains still do sequential steps of that sort, and I think that in the end everybody's going to have to move to something where either the sequential steps are tracking the correlated errors, or they're doing a simultaneous fit of this kind, and I think it's clear that is a possible source of error. Now, when you do that, that means that you will, well, first of all, that you actually do need to be trying to be as creative as possible in collecting all the systematics so that you can be doing them all simultaneously. Also, in this particular case, you're using a model of those systematics, and I think that's probably something that will have to be done in many cases, where you come up with some extra parameterizations that that allow you to model this whole host of different systematics, and then, since you don't necessarily know whether you've captured them well with that particular model, you usually have to compare it to other models and make sure that you're not overly sensitive to exactly how you model the systematics. When you do that, the systematics then turn into a part of the statistical chain that keeps track of all the correlated errors, and that's what this kind of work has led to. Now, there are some of these terms in this systematics list for this current unity analysis, which have been around in previous cycles, but have been neglected sometimes in other analyses. So, there is this issue of trying to make sure you're comprehensive in what we know some of the what turn out to be fairly important systematics are. It's possible, we don't know for sure, and that's being studied this summer, but we think that it's this combination of doing the simultaneous fits and including every one of the systematics that has led to the difference between what you see as the contours shown here in the middle contour here. That's the one from the Union. The Union is the orange one, and the ones from the DES 5-year, as opposed to DESY institution. And it's interesting to ask that question because the orange contour has a significantly bigger error bar, even though it has a larger number of slightly better measured supernova. So it's clear that's the analysis that led to the larger error bar, not the supernova measurements. And so if that really turns out to be true, then what we're finding is that it's the larger contour is what happens when you take into account these correlated errors and some of these extra errors in the systematic list. And that's something that this summer they're right now developing a series of simulations that capture a wide variety of these sorts of errors that they can be fed through these different analysis chains and compare which ones get back the simulated expected the inputs into the simulations. We're hoping that will clear up this difference. It happens to be the case that just by nature of chance that although the error bars were bigger for the Union one, it happened to have its central value a little bit further away from lambda CDM. So therefore, the Union 3 was the 3.5 sigma when combined with BAO tension, and the DES 5-year was 3.9 sigma. So they were both actually giving you comparably strong sense that there's something of interest going on here. All right, so the good news is that from this particular point of view of this one mystery, or excitement, is that we don't have to be waiting that long until we get to hear a little bit more. As I mentioned, the DESY collaboration is expecting to be coming out with their 3 times more data from the 3-year, and starting to be working on it just during this coming year. So we'll hear more from their side of the story soon. The supernova side of the story, I think we're also expecting to get some nice new results soon. And here, when you ask what redshifts will be most important, this is also another version of that same plot that I think Marek might have shown, where this is the one from our Union 3 paper, where we're looking at where are the deviations from the 0 line there is the closest lambda flat CDM line, whereas the red dashed line is the best fit to the data. And you can see that at the very lowest redshift end is going to be important, but also the high redshift above 1 is important, where the error bars become huge. So we think both of those actually we will learn much more about very soon. So at the high redshift end, there's 2 sets of data that are coming in. One is the set from the sea change data set that we worked on using clusters with the Hubble Space Telescope, and there's about 25 supernovae from there, and at least another 25 of that comparable, well-measured with a Hubble red coming in from the Hypersupremecam program that our French colleagues are finishing up now. And so we expect that we're going to have some fairly well-measured supernova in this very high redshift range appearing on this Hubble diagram very soon, and within this year. And then at the low redshift end, as we've been hearing, there's going to be much more data coming in. We have some 300 more of that supernova factory data that's been actually very well calibrated against CalSpec, and we have good confidence in that. That will come in, but then of course it'll be dwarfed by the ZTF numbers that we were hearing about today. And so we're looking forward to the fact that at both of these ends of this diagram, we will know much more from the supernova, and then we'll be comparing it to a much better measured BAO. And it seems like it's prime for hearing an answer. At that low redshift end, also, we believe that LS4 will be turning on soon. And so we've heard it mentioned a few times today, so I just wanted to put up the 20 square degree focal plane picture there. And it's obvious it's a nice calibration of many groups. We were teasing Peter Nugent yesterday at dinner, for some of us who were there, about the fact that he is unfairly persuasive when he makes his arguments for this. But it's also true that he's unfairly good at running these nice surveys, and so we're looking forward to it. So he was persuading us at LBL at Berkeley to join in on this, and it's become an LBL project as well. And so we're hoping that it can do at the low redshift end the kind of cadences that LSST is not really currently designed, intending to do, so it'll fill in there. But of course, this is really a real product of a follow-up of all the work that we've been hearing about ZTF. And so in some sense, it's that combination of the expertise from ZTF carried now to the southern hemisphere that we think will be exciting to see. Okay, next we'll have our the following 3 years, we start expecting to see even more of the numbers, of these huge numbers that we've been talking about, coming in from at the lower redshift. Once upon a time we used to call that high redshift, but now this is lower redshift below 0.8, and then with Roman we'll be seeing the work coming in from redshifts up to 2. So there we'll be finding these tens of thousands and more of supernovae, but it's worth noting, since I did talk about the spectroscopy twinning, that they are by themselves not really aiming for that kind of capability. And so we're talking about looking in many other routes to being able to obtain the spectroscopy to join in this part of the project. And so at the lower redshift end, DESY and Foremost are expected to be able to play a good role. We're still doing more work with the 2.2 meter in Hawaii and automating that. We're working on putting in sensors that will allow some spectroscopy at the Tau new 6.5 meter telescope that's now being commissioned. The Subaru, of course, PFS is coming on, and that has time committed to follow up Roman with spectroscopy. And then Roman itself does have a prism spectrograph, and that was the little part of spectroscopy that's still left over there. And so we're thinking, at least for the lower half of its redshifts, we might expect to be able to do twinning that way as well. And then we're also looking at other further options. I'll just comment that for those instrumentalists in the room, there's a lot of new technologies that we all should be tracking. I was really interested in Mansi's talking about the new capabilities for the infrared. Here's something that we're working on right now, which is a new IFU spectroscopy concept, which takes advantage of the fact that there are now amazing capabilities of this. In this particular case, it was a Canon 5-axis milling machine that can carve out these micro. In this case, these are the little mirror arrays that you do to get a spread slices for spectroscopy, and these are tiny millimeter scale and below mirrors, but they're carved so that the surfaces are all of optical quality, and so you don't have to polish them or anything. They're carved at optical capability. In this particular case, we were designing a 3-field system that can give you three different scales that you see in the upper left there, and fill in a focal plane. And so it's the world is updating in a number of different ways that we can do even better in the upcoming years. All right, so you can see where my sources of optimism are, that I think that these are some of the ways to think about the big pictures. The different groups are already, I think, taking on this challenge, and some of this, from top to bottom, is being done over again. For example, we're having great conversations with our Paris group friends who are trying to take on all these all at the same time, and we're and the different groups are contributing different parts of the story. So I think that we should be able to constrain the systematics at the level that will make it interesting to be getting these large number statistics. I leave you then with just the interesting thought about the fact that this particular tension, as I said, we would not be excited about it if we went from 2 sigma to 4 sigma with a single technique. But in this case, we went from 2 sigma to 4 sigma with 2 different techniques that have very different systematics put together. So that makes it a little bit more interesting. It's a rather unusual place to be in terms of if that really turns out to be where the WWA is. The whole family of quintessence models that are thought of as being the Thoin models are not really quite at this location. They're significantly apart from this. So the quintessence model that fits this kind of data is what they call one of these very steep hill potentials, and you have to actually start with the field right at the top of that hill. So it's a very special place to begin. And so from the theorist's point of view, it's a little bit worrying, but of course from us observers' point of view, that's what we want to do. We want to worry the theorists, and we want to, but ideally, give them something that they would trust enough to be worth putting their time into figuring out why do you get that particular quintessence model, if that's true. And so that's our job, of course, to come up with something that you would trust enough to have a whole field, of theorists work on the problem. So I think I leave you with that sense that we have now the first hints that we're at a stage where we could, in principle, begin to talk about dark energy models that were not lambda CDM, and we could actually begin to tell them apart, and that we have a fighting chance to be able to control the systematics well enough if we take it seriously, so that if we do get results like this, it'll be worth the theorists diving into it. So let me stop there and see if any questions.
Thank you, Saul, for leaving us with the theorists worried and the observers optimistic. Let's see if
always a good sign, right?
Let's see if the audience agrees. Adam, you start.
Okay. So, let's see, I'll try to provoke you a little bit here. So I'm guessing you worked on Union 3 or were involved in that, so you probably feel, and I think as you presented, you probably feel better about Union 3, let's say, than Pantheon. Plus, it has a stronger tension, 3.5 sigma versus 2.5 sigma. So is that, when you fold in that fact, do you feel better about it?
Yeah, I mean, I guess I would. You have to say I feel better despite it, right? If that were the case, but no, I think that to some extent, the odds of where the central value would be, these things sometimes they look like a stronger tension or a weaker tension, just depending on what happened to be the value, and then how quickly did the standard deviations separate from it. I think that this was done with a lot of conservative numbers put in to the priors, etc. So I did feel like at least that was done right. Now, the supernova by itself was as I said, from the union result, only a 2 sigma deviation from lambda CDM. So nobody was jumping up and down. We were saying it's I think the word was mild. That's right. It was a mild tension. You don't take an aspirin necessarily for a mild headache. So I don't think we were that worried by that. I think what's more interesting is the fact that we are starting to see this convergence from other techniques. But you still would want to wait for the fact that we're within a year of actually seeing stronger data from both low and high redshift supernova and from the BAO.
So I was curious about the prospects for Roman. So Roman, the wide field instrument will have a slitless spectrograph.
Yes.
And the last I heard, the plan was to also include spectroscopy as part of the nominal time domain survey. So is it fair to say that for 1A cosmology purposes, the spectroscopy bottleneck is solved in the case of Roman?
Problem is that we lost the it had an IFU originally, and for various bad budget reasons, it was lost a few years back, and so the prism doesn't have the same signal to noise capability all the way to the high redshift range. So it starts to lose the capability of doing things like this at around redshift 1.2, we believe. Although the same, we'll have to keep pushing and see whether we can get it further out. Some of the supernova will be covered, and then of course there's always the political pressure to just do more supernova. And so as opposed to do fewer supernova, but with spectroscopy. So that's going to also be a big tension that we'll have to figure out whether we'll get enough covered that way.
Anders. You said here at the end that this is a bit strange place to be in quintessence theory.
Yeah.
So where would be less strange to be?
So when that thawing line is, there's a whole family of quintessence models that don't have to be specially tuned. So that's a line that could have been. There's also a line that goes up to the right, which is a freezing line, and that one you could also have been. The theorists would have been more comfortable with it. But theorists come and they change their minds on these things. So I'm not yet worried about that aspect of it as much. But it has been pointed out that this is not that wasn't the place that was first hoped for. Yeah.
I have a question there.
Up top.
Brody.
Right.
Over there. Sorry.
So, one, obviously, I really love the Union 3 results, and I'm going to ask a teeny bit of a controversial question. So, Union 3 and Pantheon Plus as well were all spectroscopic, whereas DES 5-year was photometric, and you can make some arguments that maybe in DES we underestimated our errors a bit. I would disagree, but it's a fair argument. So I guess my question to you is, if we're doing this well with photometrically classified supernova, why do you think that we need spectra going on in the future?
No, it's a really good question, and I think that for me, if we got answers that were not controversial, like if we did not see surprising lambda CDM tensions, etc., I think people would tend to be willing to just go along and say, okay, that's probably a good measurement. Everybody agrees with something simple. But as soon as you start seeing that anything that is really going to force the theorists to get out of bed, and go to work on it, then it seems to me that it puts the ball back in our court, that we've got to be able to stand by that we aren't seeing any population drifts with redshift, and that we aren't accounting for. And we do know, for example, that when we looked at these 3-parameter spaces that separate out the supernova in spectroscopy, that they're degenerate for some of the light curves, where you can have 2 light curves that have the same stretch and the same color as each other, but fall in different places in that 3-dimensional space. And so if the population's drifted across that kind of dynamic without us knowing it, that would be a reason that you'd really want spectroscopy, not just photometry.
So on a kind of follow-up from that, I think one of the powers of this plot is that there are 3 separate surveys with 3 separate analysis chains to go with it. How do you think we deal with that coming into the future? Because in some way the community all works together in one big survey.
Yeah. Well, a couple thoughts there. One is, I think you've pointed out one of the funny features of going through a life where I spent most of my first half of my career trying to convince the astronomy tax everybody to allow us to work together and to let people join forces. And then I started realizing in recent years that now we have the funny conclusion, which is that everybody's using the same data sets often, and they're often using the same software, and they're often using the same arguments to convince themselves of what they're going to observe, and that you're not getting quite as much of the separate teams doing their own complete analysis chains without open source software that everybody's sharing. And so bugs in the software are going to be there for everybody if we're not careful. So I think that's a very interesting point. But I will say that just to make sure, have everybody hear the lunch table discussion that we were having with our French colleagues. This idea of doing a completely independent supernova measurement is now possible with combining the ZTF dataset, the SNLS 5-year parts that were not already used, and then the HyperSprimCam Subaru datasets. That one can be done as a completely separate analysis chain, and I think that's actually going to be fun to see what you get from something like that. And of course, as we all think about our future surveys, we should always keep in mind the possibility that we should do some analysis chains that are just done completely independently from other analysis chains, so we don't end up with the hidden bug that everybody has.
Were you also optimistic, Nicholas, after the lunch discussion?
Couldn't be more optimistic.
Any final questions? Yes, Mickael.
Yes, so you've been very active for the computing side, with the BIS, for instance, in Berkeley. I was wondering if you can give us your thoughts about where we are going in the future for computing, astronomy, where students should go. What is the interesting thing you think we should focus on for the next few years?
I think it's going to be really interesting to see what do we find ourselves using and what do we find ourselves not using in the AI world, right? And of course, there's the interesting observation that we all were sort of a little bit shocked at what the generative AI was doing with language in this last year and a half period, and that's offered us the capability of doing some nice like programming. It actually helps with programming very nicely in some ways. But of course, for our analyses, we already had been using a lot of machine learning techniques previously, and we don't know yet whether or not using some of the same attention mechanisms that were used for this large language models might end up making our machine learning much more effective for some of our analysis techniques. That's something that's still new, and it's not clear yet what will be, how strongly we'll get effects out of that. But it's certainly clear that taking advantage of all the every time we learn something new about how to do statistics, like the hierarchical Bayesian modeling, the ability to hunt through huge parameter spaces that really wasn't the case 15, 20 years ago, but between the much bigger parallel computing, but also these techniques of hunting through these chains as we can do now. I think this is something that students should be keeping their eye on. Each of these different tools as they become available. It's worth staying on top of them and just playing around with them and trying them out as they come out. I think because they do offer us ways to deal with much larger data sets, but also statistics that require running essentially mock versions of your entire system thousands of times, so you can figure out really where the statistical strengths of your measurement are. So I think all of these things are exciting. You can also use the AI nowadays to mimic the full simulations, so you can do many mock versions of your analysis with much more speed. And so I think statistically that can really help.
Great. So I think we should end this session with a big applause, not only for Sol, but for all the speakers of this session.